Okay, I think we are going to start. Please take your seats. Welcome everybody at the last day of our conference, first session. We have 3 speakers this morning, variety of topics, and we will start with Vitor Cardoso from Lisbon telling us about the evidence for black holes.
Thank you. It's a great pleasure to be here. I'm very thankful for the invitation. It's been a great meeting. These are the right times to question fundamental issues. For example, how many black holes there are, where are they, how were they born, how they evolved, or what's the graviton mass or graviton speed. And most of these issues actually involve black holes. For example, so we're at the right place. Do we know that black holes, that objects that look like black holes in nature, really are described by the Kerr family of geometries? Can we constrain alternatives to Kerr using observations? Do we know if cosmic censorship is always preserved or not? And I'm going to focus only on one of these issues today, which is to what extent we actually know that we're dealing with black holes. Okay? So how sure are we that if we take a merger of compact objects that LIGO has seen, for example, they are really black holes? Now, there's, I think, 3 ways that you can go through my talk. The first one is to think that I'm just a crackpot that doesn't believe in black holes. That's the wrong way. Okay? The second way is to finally get a sense of how you're able to quantify the statement that we see a black hole in nature, of a certain mass, of a certain spin. What evidence do we have for it? So I'm going to try to quantify the evidence for that. So that's one possible way that I would like you to look at this talk. The other possible way is to understand mechanisms or strategies to look for alternatives, if there are any out there. Okay? There's different ways, or there's different reasons why I think we should take this seriously. The first, of course, is that this has been discussed at length. The black hole exterior is perfectly regular, the interior is not. Even semi-classical effects are not fully understood, for example, the information paradox. Some solutions to that involve non-local physics that might change in a soft or in a hard way the near horizon geometry. And I think there's always implicit the assumption that if and when quantum effects kick in, they will appear at the Planck scale. The Planck scale being some combination of Newton's constant and C or H, but it's easy to cook up an effective Planck scale which is different. For example, by using extra-dimensional universes. But in fact, even if you stick with the usual and standard Planck scale, some surprises might show up. One of them, I think it's an interesting work by Bekenstein and Mukhanov, where they try to quantize the black hole area, and you realize after you do that even at this level, black holes are not perfect absorbers to an extent that it would show up in LIGO detections. Okay? It seems like a fantastic prediction. It arises because they conjecture an equally spaced area spectrum for black holes, so it doesn't arise in all theories, but still, I think it's something to bear in mind. Of course, we know dark matter exists. It plays, well, it's an important component of our universe, so there might be, for example, dark matter clumps which can or not be very compact and behave for many purposes like black holes. But if you're not satisfied with any of this, then forget about all the motivations and just think we have detectors. Physics is an experimental science. Let's go out there, observe, and quantify. Okay? Now, since I'm going to talk for most of the time on alternatives, let me show you how a compact object would look like if you slice it and you look at how matter moves. Okay, so this is a slice, an equatorial slice of some compact object, okay? Far away from the object, you have Newtonian physics, so planets and stars move on stable circular motion, for example. Then relativistic effects start becoming important. You have an innermost stable circular orbit, so anything that approaches this will quickly plunge into the object. There's a curious feature of GR, which is inside the ISCO, so very close to, well, to strong gravitational fields. Light, there's a special location, it was discussed several times in this meeting. There's a location where light, high frequency waves, can orbit on unstable circular motion. This is, well, I'll call it the light ring. Of course, this is a slice, so it would be a photon sphere. It's unstable, so these waves eventually leak out. If you add spin to the space-time, there's another interesting feature appearing. It's this dashed line. So inside this dashed line, if the space-time is sufficiently similar to that of Kerr, you have negative energy regions, ergoregions, where things cannot remain at rest with respect to faraway observers. And it's, well, you can use this property to extract energy from space-times, and I'll go over there in a minute. And if we're dealing with a black hole, then there's an infinite redshift surface here, a one-way membrane. But you see, because first of all, black holes are black. So it's impossible, of course, through any experiment in a finite time to know if you have this infinite redshift surface, okay? But second, there's a lot of time. There's a lot of redshift close to the surface, okay? So you can stack a lot of crazy things there that still look and may behave like black holes. Of course, if you start this program, there's a lot of things that you need to answer. And I'm going through them, and it will show you why we strongly believe that black holes are the object there. And it will also tell us how we can quantify this, okay? So the challenges are, do we have alternatives that look like black holes that are very compact and are nice in some way? Do they form dynamically? Do we have alternatives that form dynamically under reasonable conditions or not? Are they dynamically stable, or do they get disrupted on very short time scales? Do they look like black holes, when we look at them or not? And finally, if I have time, I would like to show you the current status and how I'm going to quantify the evidence for black holes. Now, there's zillions of alternatives. I think there's two in this list that are acceptable. Boson stars, these are self-gravitating configurations of scalar or vector fields. You need a mass term or some non-trivial self-interaction to produce these, but they are nice, okay? They have a good theory, they have a well-posed initial value problem. If you're willing to accept that the equation of state of matter might allow for strong anisotropies, you're also able to build quite compact stars. We don't know yet if this is prone to evolutions, if it has a well-posed initial value problem, but there's efforts in that direction. And then there's a multitude of proposals, where there's actually no underlying theory, where it's hard to work dynamically with them. Graver stars, fuzzballs, superspinors, you name it. Okay, so we do have some alternatives. The only one where we know how to deal with it are boson stars. Let me show you what happens if we try to form boson stars. So I'm going to take a Gaussian pulse of a scalar field, simple, minimally coupled, massive scalar field, and let it go, okay? Let me play this back. This is the initial profile for the field as a function of radial distance from the center. This is energy density as a function of distance, and this is a movie. So you see how it evolves, okay? There's nothing special. The initial conditions were not fine-tuned. And if you wait long enough, you will see that this looks like an almost stationary star. Okay? Some people call these oscillotons. If the field were complex, this would be a boson star. Okay? You can repeat this experiment, changing the initial conditions, and you will find a variety of boson star masses and radius, and you can build a mass radius diagram. Okay? This is the mass radius diagram for real or complex fields. These are for scalars, these are for vectors. Okay? And there's two interesting features here. The first is if you look at the point of maximum mass, okay, these stars can be quite compact to the level of a neutron star or so. If you tweak the self-interaction potential, then you can make them even more compact. Okay? The second interesting feature that you can see from this diagram, but is that these stars, when they talk to each other, if you try to make these stars interact, merge, for example, you take two stars here, very light stars, very dilute stars. If you merge two stars here, they will tend to go up in the mass radius diagram. Okay? And you could think that if they go beyond the maximum mass, they just collapse or do something weird. Okay? But in fact, the behavior close to the maximum mass depends strongly on initial conditions. If they grow through minor mergers, we have seen that the star just expels the extra material. This mechanism is called gravitational cooling, and it seems to conspire to produce stars that hover around the maximum mass, which is also the maximum compactness value. So there seems to be ways of producing very compact objects. So the question is, okay, let me assume that they form. Are they stable on relatively short timescales? And there's interesting results here. First, if you try to form spacetimes that look like Kerr, very compact, but that look like Kerr on the exterior, you immediately get into problems if you don't have horizons in the spacetime. The problems being that Kerr, as I said, has an ergoregion. It's a negative energy region, okay? And this movie shows you what happens if you scatter something off a negative energy region, okay? Let me play this back. There's a positive energy pulse on the exterior. I scatter it off an ergoregion, and you see it produces a negative energy state here, okay? Energy conservation tells you that whenever this guy interacts with the boundary, you have to produce first a positive energy state in your normal space-time, and energy conservation tells you the negative energy state has to grow in the ergoregion, okay? And this is a cascading, so there's an instability here. It's called the ergoregion instability. We don't really control the time scales for arbitrary objects, but it's there. So this is with spin. If you remove the spin of the object and you try to produce a very compact space-time, there is an interesting result by Joe Kayer a few years ago that tells the following. If you try to squeeze the object inside the light ring, so inside its photosphere, okay, then fluctuations in this space-time become extremely long-lived. They decay no faster than 1/log of t squared, okay? And the conjecture, which I think so far there's still no proof, is that at the nonlinear level, this is going to give rise to an instability. Actually, there's a flat space analog of this. There's a nice result from '98 of a Minkowski maze. If you try to trap light here, it decays in a similar way. So again, an instability probably at the nonlinear level. There's another strong argument that tells you that if you try to form too compact an object, generically at the classical level, it's going to collapse to a black hole when it interacts with other objects. That's the hoop conjecture, okay? The hoop conjecture being that if you take a hoop with the Schwarzschild radius of the object, if your object fits in all direction in this hoop, it's a black hole, okay? So now if you take an ultra-compact object and you merge, for example, at high energies with another one, at sufficiently large energies, the object will always fit in the hoop. So there's arguments that at least classically, it's hard to keep a compact object without an horizon there. Of course, there might be special properties that come with horizons at the quantum level, and therefore this is not a no-go theorem for these objects. Okay, so I think it's challenging to form compact objects, to have them stable, okay, on short time scales. So let's go and look at what happens when we look out there, okay? Now there's clever constraints using electromagnetic observations. For example, if you parameterize the surface of your object in, well, standard Schwarzschild coordinates with a dimensionless quantity epsilon, okay, you can try to impose bounds just by looking at the absence of extraordinary events. For example, the fact that we haven't seen tidal disruption events when we look out there constrains epsilon to be smaller than or of the order of 10 to the minus 5. It's a nice small number. If you look at the contrast between the interior of Sagittarius A and the surrounding accretion disk, okay, you can impose, I think, an outrageous bound on this quantity epsilon, 10 to minus 35. There are issues with this bound. Some things were not taken into account. I hope to have time to give the more precise number, but still, it's an amazing constraint. Of course, I'm here at the time of the Event Horizon Telescope, so I need to mention shadows of compact objects. I think it's clear to everybody that shadows constrain roughly the light ring, not anything related to horizons, okay? Here's an example of what a shadow of an exotic compact object looks like for a boson star. Okay, it's a compact boson star. This is how Kerr looks like. It's being illuminated by a torus. Then you take the same torus, you illuminate a boson star with the same mass and spin, and it looks like this. And I think none of us can seriously say there's a difference here. Okay, so it's challenging to use shadows to discriminate between very, very compact objects. But we have access to gravitational waves, so what happens there? How can we go around and constrain very compact objects? Now, the nature of the inspiraling objects is encoded, of course, in the gravitational wave signal. And there are several contributions that you might look for imprints of structure. For example, Kerr, black holes in GR are very simple. All the multipolar structure of the gravitational field is dictated by two parameters, mass and spin. Okay? So you might think that if there's some structure and they are not black holes, then the multipolar structure of this field is going to be different. It's going to affect this object in some different way. Okay? The tidal deformability of black holes in GR has a very special property. Their tidal love numbers are 0. Okay? And this also, of course, affects the phasing of the signal, and you might look for these imprints in gravitational waveforms. In addition, horizons are a one-way membrane. So if you remove the horizon, this is going to affect your energy balance during the in-spiral. Now, these are possible imprints. It's not easy to go there. Let me show you why. A neutron star, well, with some equation of state, okay, has a typical love number in my normalization of around 200, okay? And this is barely the magnitude of numbers we can measure now, okay? You can discriminate between some classes of boson stars just because they have, some of them, large tidal deformabilities. But if you start compressing our object too much, their tidal love number goes down most of the times as 1 over log of epsilon. Okay? You need fine-tuning not to have this behavior. So it's it's challenging to discriminate between something that's very small from something that's zero, okay? But it is possible, and I think we should try to do it. This is one example of things you could do with a space-based detector. So I have, there's a parameter, gamma here. Gamma is 1 if you're dealing with a black hole, and it's 0 if there's no horizon there, okay? And the idea is to start discriminating either using the tidal heating parameters, so absorption effects, or tidal deformability parameters, okay? And you will find that it's hard to find sources that do this, but there are highly spin, so this is spin, this is the uncertainty with which iiic can measure those parameters. It's challenging, but especially at large spins, there are, let's say, hopefully a handful of sources where this test could be done. This is in the in-spiral stage, and I would like to devote the next 5 minutes to tell you about the post-merger phase, okay? By the way, the reason, of course, a true test should take the full waveform, should evolve the objects past merger, and so on and so forth. I think it's clear that we don't have a theory yet that allows us to do this. So this is a poor man's way of testing what you have, okay? There's a claim that there's nothing other than a black hole that's compatible with the strong damping of the post-merger waveform in the LIGO signal, okay? And the reason is simple. You form an horizon, it absorbs everything it can, okay? And therefore, the signal is strongly damped. If you remove the horizon, well, then you have to have something which lives for a lot of time, right? Now, this reasoning is flawed, and let me show you why. So I'm exciting here the modes of a black hole, okay? The ring down stage of a black hole, by throwing a star, this red dot, at a massive black hole, okay? This is the gravitational wave amplitude as a function of time. And you see that the burst, the main burst of radiation, is excited when the star crosses this line over here. This is a light ring. It's the peak of your effective potential, okay? It has nothing to do with the horizon. In these coordinates, the event horizon is somewhere to your left, okay? And just causality arguments tell you that if you're able to place structure way to your left here, the initial signal has to be identical. There's no other way. These are just causality arguments, okay? And in fact, if you try to do exactly the same sort of simulation for an object that does have structure close to the Schwarzschild radius, you will find the following. So black lines in these panels are gravitational waveforms for a black hole. It's always the same, okay? Right? But now the colored lines are the same waveforms when I replace my black hole with an object that has structure at epsilon, I think 10 to the minus 6. Okay, it's something very close to the Schwarzschild radius. You'll see that the initial burst, so here, I think this is a gravitar star, this is a wormhole, and this is some very compact star, an isotropic star, okay? The initial part of the waveform, the main burst and the subsequent ring down is indistinguishable at the numerical level here, okay? Just causality. The way you excite the modes and initial burst has to be the same if your structure is located well inside the gravitational potential. And then, of course, the star crosses the light ring, it excites the modes, a fraction of these modes hit the detector, another fraction goes in, but now there's no horizon to absorb this ingoing wave, right? So it interacts with the object, travels out, it sees the light ring, a fraction goes back, another fraction goes out, and in practice what you get is a series of echoes of the original burst just because you're in a finite height box, okay? So it's just like my sound waves here. And in fact, you don't even need to merge these guys. So if you scatter the same star off this object, it's not even colliding, okay? You see exactly the same. Black line is black hole waveform, red line is the waveform for a wormhole. And again, the same kind of structure, late time echoes in the waveform. So of course, a good strategy then is to look for this structure in the waveforms. Okay, let me take the rest of my time, I think I have 2 minutes, to show you how then you can answer the question of how to quantify the evidence that we have black holes in the spacetime. Okay? For example, if you use light ring measurements, shadow measurements of Sagittarius A or M87, you're really constraining, you're really telling me that there's a light ring in the spacetime. Okay? Right? So your epsilon will be over the 1. Let me use a different discriminator. I take a photon, I throw a photon at the object, okay? And I measure the blue shift of the photon as it goes inside the gravitational potential, okay? I'm showing you here the minimum blue shift of the photon before it encounters any possible structure that we haven't seen so far, okay? Right? So measurements of the light ring, for example, give you a blue shift of order 1. Okay? If you use the LIGO consistency with the ring down of a black hole, then you know that your photosphere is relatively clean. There's no structure close to the photosphere. And this gives you a minimum blue shift of a photon before it encounters anything of order 10. And you can go down in this list of tests, okay? If you're able to constrain the absence of echoes within a few seconds of the main burst, then you're going to be placing a constraint of 10 to the 23 on the minimum blue shift that a photon suffers before it encounters anything, okay? And Lisa, if you believe the forecasts, the constraints on the spin-induced quadrupole moment will give you a constraint on this blue shift of order an exponential of 5,000. It's unbelievable, okay? Or if you want a constraint on epsilon of exponential of minus 10 to the 4. So I think this is the way, one way, a good way to go around and quantify the evidence for black holes. And let me finish by saying, again, these are really remarkable times. It's the opening of a new window, and I think a lot will be learned from this. Thank you.
Thank you, Vitor. Questions, Ramesh? Oh, you need a mic. Sure.
So very interesting stuff, Vitor.
Thank you.
So there's one problem that when Avery and I and others look at the electromagnetic signal from a surface, or when you look at your gravitational wave echoes, we have to always assume some property or a boundary condition at this surface, right? So we have to assume, for instance, that if you drop stuff, it will re-radiate. If you tell me that the surface can absorb, even though it's not a black hole, if it can absorb and it's got infinite heat capacity, then of course our argument is dead. And similarly here, I think if you are allowed to change the boundary condition, you can probably kill the echo completely. So I was just wondering, are there any fundamental constraints that one can use on these boundary conditions or whatever additional constraints?
So so of course at some point if you start changing the boundary conditions, you will get something that is a black hole for all purposes, right? So there's a lot of caveats that come with these values. They almost, as you were saying, almost all of these numbers assume something that reflects substantially the gravitational waves. We don't know of any material actually that absorbs well gravitational waves, right? So I think it's a sensible assumption, but you're right. I mean, if you start displacing the surface, but changing its properties, you get something that looks like a black hole for any purpose. And I think, yeah.
We'll have one more question, and if you could pass the mic.
Isn't any consideration that, say, a black hole might start its life as a normal black hole and then as it evolves becomes, say, a compact object without an event, basically would only have an event horizon early in its lifetime?
Sorry, can you repeat the question?
So would it start its lifetime as, say, having an event horizon, and then as it evolves, it would become a compact object?
Yeah, there are well, suggestions that Hawking evaporation could do this, but the final remnant is going to be very, very light, so I don't think it can be used for this type of purposes. I am not aware of any other mechanism that could remove the horizon.
Thank you.
Let's thank the speaker again. And our next talk will be from David Wallace, who will tell us about firewalls and decoherent histories.
Thank you. So this is going to be a bit of a change of direction in that I want to talk about some of the quantum mechanical properties of black holes, or at least what seem to be some of the quantum mechanical properties of black holes according to the best we currently have in terms of a grasp of the quantum theory of gravity. I specifically want to talk about some thoughts about the firewall problem. Given that this is a sort of as much a conceptual as a technical issue, and given the nature of the audience and given the nature of my own specialty in philosophy of physics, I think maybe one thing I can contribute to this is to try to give some kind of statement of what's going on in the problem in a way that's as clarifying as possible as to what some of the assumptions are, and perhaps accessible as widely as possible to the very interdisciplinary audience we have here. So with apologies to the experts here, I'm going to spend a reasonable amount of this presentation talking about the general nature of the problem and its assumptions, although I'll say some things towards the latter half of the presentation that kind of gesture at some thoughts towards ways in which we might be able to understand what's going on with the paradox. Okay, so my starting assumption for how we want to think about the quantum mechanics of a black hole is the sort of entirely formal theory you write down if you take general relativity with some placeholder matter field and you build a quantum field theory out of that in the most naive possible way, which is to say you just write down the path integral for that theory and use it to calculate transition amplitudes, partition functions, and all the other things we normally want to get out of quantum field theory. Now, we already know if you write that object down that it's in various ways pathological. It's been known for a very long time that this is a non-renormalizable field theory. Back in the old days, the reasoning went, this is non-renormalizable, therefore it's bad, therefore we should run screaming. These days, we tend to have a rather more relaxed attitude to issues of renormalizability. We're more likely to say something like, well, no quantum field theory should be trustable on arbitrarily short length scales. Any quantum field theories, path integrals have to be regularized by some kind of high energy cutoff to make the path integral even well-defined. And the existence of non-renormalizable terms is evidence to what that new physics looks like that introduces the cutoff, because it tells you roughly the scale of the cutoff. And so the reinterpretation of the fact that the interactions in quantum general relativity are non-renormalizable is that the cutoff ought to be somewhere at the scale of the Planck length. And so as long as we consider phenomena which don't probe down at the Planck length, then defeasibly we might hope that the path integral description is a reasonably good description. The problem is that evaluating path integrals is kind of difficult, which is to say basically impossible except in certain perturbative regimes. And the normal perturbative regime we use is some kind of saddle point approximation. So I look for some localized extremum of the path integral. I take a sort of quadratic and higher term expansion around that, and then I use perturbative methods to work that out. And if we do that with quantum gravity, if we do some kind of decomposition of the metric into an initial part G naught and a variation H bar, and if we introduce the square root of G to get the units right, And we expand the action of general relativity in this framework. Then we get an approximation to the path integral that, long way down, so that looks something like this. So I've got an action here in which we're not integrating over the G naught term, we're integrating over the G integral should be an H here, we're integrating over that perturbation. So we have something that looks like a quantum field theory written on a background space-time G0 with a field for the matter and a field for the graviton, perturbations around that, but with the additional constraint that the choice of the G0 extremizes the path integral in the sort of appropriately more careful quantum way. And what that translates to is a condition on G0 that looks like this. So I've got the variation of the Einstein-Hilbert action plus the expected part of the variation of the matter field action plus the expected part of the variation of the deviation bit of the Einstein-Hilbert action must equal 0. And we know that the variation of the action is the stress energy tensor, and the quantum expected values of variations of the action are expected values of the stress energy tensor. So we find our way to semi-classical gravity. We have a theory where the geometry has to satisfy a consistency equation where I do quantum field theory on the geometry, which is linear, but I have a sort of nonlinear back term because I need the expected value of the stress energy tensor to satisfy the Einstein-Hilbert action. And we have something that's formally very similar to the kind of way one does some semi-classical electromagnetism, where you treat the electric field as a background and look at the back reaction of that on quantum particles. Okay, so that's the starting theory I want to set up, and I've laboured that a bit because I think we want to see what the presumptions are that are going into the claims that are made of black holes in the quantum gravity literature. Okay, so why are black holes interesting in that context, and why are black holes such a focus of attention in quantum gravity more generally, and in this kind of style of quantum gravity in particular? Well, I take it the exciting thing they offer is something like the following. If we look at the exterior region of a black hole, then we find that we've got a consistent quantum field theory description, and the ultraviolet phenomena, the stuff that happens when the quantum field theory breaks down because we're going outside that cutoff region, outside the region in which it's safe to use it, is happening at the horizon of the black hole. But we also have a consistent quantum description of the interior plus the exterior, and on that description, the ultraviolet physics is happening in the vicinity of the singularity, and the horizon is low energy and well behaved. So the duality between those two descriptions, the need for them to be mutually consistent, effectively means that we get some very strong constraints on the ultraviolet features of quantum gravity coming from the low energy description of the horizon from a different perspective. And then from that point of view, the information loss problem and the more modern version of the firewall problem, you can think of as being about quite subtle incompatibilities or apparent incompatibilities between the interior and exterior description that seem to threaten this kind of nice story. So to spell that out a little bit, we're interested in this kind of space-time description. We're interested in looking for solutions to that semi-classical description on this kind of space-time setup. So I've got infalling matter forming a black hole, forming a horizon. But we're really only interested in this in the late time region, after which the sort of perturbations from the formation of the black hole have died down. So we can time evolve that forward. And the limiting case, we're really considering quantum field theory on the right-hand side and the top part of the extended Schwarzschild space-time with the matter that formed the black hole relegated to not much more than a boundary condition on the diagonal of the diagram. So that's the space-time we're interested in. And as long as we're just doing the exterior part of the field theory, we're really only interested in this part of the space-time, the exterior part. We can foliate that in the usual Schwarzschild way. We can construct modes of a linear field on that space-time. We find that because of redshift, essentially, then for a given mode of given asymptotic energy, then the locally measured energy gets larger and larger as you approach the horizon. As you approach the stretched horizon, those are the modes, as you approach the stretched horizon, where the local wavelength reaches the Planck wavelength, or the proper distance to the true horizon reaches the Planck distance, then you reach a regime where the field theory ought to break down, which is to say you should only really trust quantum field theory to the right of the stretched horizon, to the right of the red line. And since this is a theory of space-time, that effectively means that in this kind of description, you shouldn't really take seriously anything on that side of the diagram at all, from the point of view of trying to look for solutions to the quantum general relativity that take that space-time background as the background around which you want to expand. And if you look at the structure of the semi-classical equations for that, then we know that the Schwarzschild metric satisfies big G equals 0. So we need the expected stress energy tensor to be 0. That means we need to keep track both of the potential excitations to the quantum field, of the presence of particles and the like, and of the existence of any vacuum polarization that's happening, because quantum field theoretic vacuums aren't empty space, they aren't nothing, they have their own associated energy momentum. If we do that, the most straightforward thing we might imagine is, if I've got wave function modes coming into the black hole from spatial past infinity, and if I've got wave function modes starting on the past horizon, your natural starting point is to say, well, let's suppose that neither of those modes are excited, so I've really got what you might naturally think of as the vacuum for that space-time. What you find then is that there's very strong vacuum polarization, getting stronger as you approach the horizon. So the semi-classical equations are wildly violated in the vicinity of the horizon, which is to say we didn't actually succeed self-consistently in describing a piece of semi-classical gravity in that framework. We tried the sort of guess and check thing. We tried guessing Schwarzschild exterior space-time. We tried guessing the Boole-Ware vacuum. We did the quantum field theory on that space-time, but we badly failed the consistency conditions, so we didn't find a solution. Famously, if you instead put both the in and the out states in thermally excited states at exactly the right temperature, then you find that the positive contribution to the stress energy that's coming from the thermal modes exactly cancels the negative contribution to the stress energy coming from the vacuum polarization. And so you get out the fact that close to the horizon, the stress energy tensor vanishes, and so at least for the near horizon physics, the Schwarzschild solution does solve the semi-classical equations. So that's a solution that works. And it corresponds to the black hole sitting in a bath of thermal radiation. If instead you say, okay, let's leave the in modes, the modes which would be starting from the past horizon, unexcited, but the out modes excited, which is to say have a situation where there's thermal radiation coming out from the black hole, and we get the temperature right, then we come pretty close to solving the semi-classical equations. More precisely, we come wildly far from them as we approach negative time infinity, but that was the point to which the matter boundary conditions messed with the story anyway. In the late time regime, we still have something that basically solves the equation. And that gives us a decrease in the black hole mass, or it ought to give us a decrease in the black hole mass because there's a flow of radiation energy out. And so we need to keep checking our self-consistency rules here. And to see if that kind of solution is self-consistent, we have something like the following. Well, firstly, all this had better be happening such that energy is conserved. It had better be the case that as the energy flows away, and as I work out how the mass of the black hole would have to decrease to conserve energy, I do it while maintaining those consistency conditions. You could imagine deviating away from it as the system evolved, in which case you wouldn't have an entirely consistent space-time. That works out fine. It had better be the case the mass is changing really slowly, or slowly relative to the field theoretic constraints, because we were solving this on static Schwarzschild spacetime. We weren't solving it on a non-static spacetime. That also works out fine. And we better make sure the whole system is evolving unitarily, just from the normal preserving the rules of quantum mechanics. There's room to challenge that, but inside the normal framework of quantum mechanics, we want to make sure the system's evolving unitarily. And that's fine, provided the stretched horizon, which is a place where there ought to be quantum degrees of freedom, but where our theory is failing to describe them. It had better be the case that stretched horizon has the right kind of entropy so that the whole evolution can stay unitary. you can work out what that is, and if it turns out that the stretched horizon has that quantum mechanical entropy, then you get self-consistency. And of course, lo and behold, that entropy is also the entropy that we were led to by thermodynamic considerations of black hole radiation. It's also the entropy you get if you just brute force calculate the partition function and thereby the entropy using the path integral we started with. So we have a satisfactorily self-consistent description of what's going on in the exterior. And of course, famously, that exterior description seems to be a description of the black hole as an entirely thermal system radiating in an ordinary quantum mechanically thermal way. But then you consider, okay, what about the description from the interior, where I want to consider, how does the physics look to an observer who falls towards the horizon, who we don't expect to see anything interesting in the horizon at all? So we now say, let's try doing quantum field theory not just on the exterior, but on the entire exterior plus interior region. There's a whole bunch of ways of doing it, but one quite illustrative way is instead of considering foliating the exterior space-time by the Schwarzschild slices, I foliate it by something like limeric coordinates, which measure the infalling observer's time. And these are coordinates that look like the Schwarzschild coordinates at large distances, but kind of deviate sharply away from them as you approach the black hole. And if you do the quantum field theory from that point of view and you do a mode analysis, then you don't find anything singular or weird happening at the horizon. You find the total number of modes are conserved on any given slice, but left-moving modes are falling into the singularity and being removed from the theory. On the horizon, there's a lot of tidal effects going on, so modes in the vicinity of the horizon get redshifted down. Since we've got our cutoff in place, we weren't permitting in the theory any modes above the Planck wavelength, so we actually have new modes just coming into existence on the horizon. How do you stipulate how they ought to come into existence? Well, the theory doesn't give you a principal way of telling you, but if you assume the equivalence principle is right, then the physics on that boundary ought just to look like the local vacuum or something quite close to the local vacuum for an infalling observer. That forces there to exist entanglement of a particular form between those modes. And that means in turn that if you consider how this all gets described by an external observer who doesn't have access to the interior and so traces over those modes, they get something that looks thermal, and looks thermal at just the same temperature that we got from this rather different self-consistency approach that we were using for the entirely exterior description. So that all looks very satisfactory. It all looks as if we've got a mechanism for explaining actually how the thermal radiation is being generated at the boundary that's consistent with, albeit kind of subtly different in its apparent description, with the high-energy thermal description we were getting out from the exterior quantum field theory where the cutoff's appearing at the horizon. But there's a problem. And the problem comes from the fact that that story about the generation of entangled pairs at the boundary and thus generating thermal radiation says that they should always be entangled all the way through. And so that says if you want to consider how the von Neumann entropy of the radiation coming out of the black hole evolves, then I'm just adding black body photons to it. So it should just be going up and up and up in a smooth fashion. So that ought to be describing the entropy of the exterior, and turn that around and consider that the whole system starts in a pure state. That also ought to describe the entropy of the black hole system itself. So that should be going up and up. But of course, the maximum entropy a quantum mechanical thermal system can have is given by its microeconomical energy at a given microeconomical entropy at a given energy. That's going down and down as the system's degrees of freedom fall. And so at some point you reach a contradiction where this assumption of generating black body radiation leads to a prediction the system's entropy ought to be larger than the maximum entropy it's allowed to have. And so consistency would require at this point the radiation to stop being black body radiation, to start being entangled with early time radiation, and eventually to go down to zero, so that the whole evolution process takes us from pure states to pure states. And then page time is the term for when that happens. And that seems to cause trouble for that story about what's happening in the interior description, because if that's right, then late-time photons coming out from the horizon need to be maximally entangled with late-time photons somewhere else, early-time photons somewhere else, and therefore can't be entangled with those mirror modes inside. And so it seems, theatrically it seems as if therefore it had better be thermal at the boundary, therefore there should be a firewall. More mundanely, it seems like just something has gone wrong with the quantum field theoretic description of what's happening in the in the interior description. And that's concerning because that now seems to undermine the self-consistency of the whole story. So the way this often gets described in the literature is, just put a statement of the frame, it describes the literature as this is a failure of low-energy quantum gravity and quantum field theory in a regime where we shouldn't expect it to fail. And I want to put a little pressure on that description of what's going on, and this is part of the reason I labored the description in the early part of the talk. Because when we talk about low-energy quantum gravity failing, I mean, this is sort of picking up on some of the themes in Jim Weverill's talk, I take it we mean something like this, that we expect that to happen when we have energies of the order of the Planck mass, wavelengths of order of the Planck length, curvatures of order of the Planck curvature, and the concern is, well, none of those things seem to be happening in the vicinity of the horizon, at least not from the point of view of the infalling observer's description, so we don't seem to have any grounds to expect the description to fail, and yet nonetheless it seems to have to fail. But of course what's failing isn't simply the low energy description full stop, it's the semi-classical approximation within that. We're assuming in this whole story not only that we could use the path integral description of quantum gravity, but that we were specifically looking at the solution space gained by perturbing around particular fixed classical backgrounds, or not necessarily fixed, but determinate classical backgrounds. And if we ask for the conditions in which that semi-classical gravity might fail, they're much more mundane. We'd expect that to fail whenever we're somehow forced to consider path integrals that non-trivially sample more than one classical configuration, or more generally that involves some kind of situation that ought to be described as a macroscopic superposition. You know, I can construct a situation that violates semi-classical gravity much more cheaply than I could a situation that violates the assumptions of low-energy quantum gravity. To violate the assumptions of low-energy quantum gravity, I need to generate Planckian scales of energy or curvature or something like that. To violate the predictions of semi-classical quantum gravity, I just need to toss a quantum coin. If it lands head, stand on this part of the room, and if it lands tail, stand on this part of the room. You know, at least inside the unitary description, I need to describe that as something like a superposition of the geometry induced by me being over here and of the geometry induced by me being over here. Now you can try, you can describe that as that perturbatively around the same background because I'm not actually that heavy, but if in more strong field regimes and more generally in places where we're not quite sure what's going on with that expansion, then we've got grounds to feel something subtler can be going on, and grounds to think that the semi-classical description can be failing without the full quantum field theory description failing. And to sort of hint that something like that may be going on here, I just want to explore a little bit in the last part of the talk some of the sort of slightly surprising quantum mechanical features of how just an ordinary thermal system can radiate even if we assume it's not a black hole, and show that some of those subtleties are at least suggestive for the idea that what's going on in black hole evaporation in the firewall context ought to be thought of in some sense as some sort of quantum superposition of lots of semi-classical goings on. So here's my sort of model I want to think for a thermal system. I've got a system HS whose Hilbert space is relatively small. You know, a red hot iron ball will do fine. And I've got the environmental Hilbert space, which is something like all the modes of the radiation field in a box around the hot object or something like that. And why should we expect that system to cool by emitting black body radiation? Let me model this for simplicity by just thinking this is a finite dimensional system, so I don't need to worry about expected energy or something. So the analog of black body radiation would be sort of the emitting of perfectly mixed quantum states from the system. So I'm thinking of some kind of model where I've got I've got a picture of this later. I've got something like this situation. So the system is spitting out, let's say, spin-half systems or qubits. And we're interested in why we'd expect those qubits to be spat out in a thermal state. Now, of course, in detail, if you want to know exactly what the radiation from some physical system ought to look like, there can't be a general argument that it must be black body, because sometimes it isn't. There are absorption lines and things like this. But the sort of general default assumption as to why we expect black body radiation tends to go something like this. If I think of how my radiation is playing out, I can think of myself as just breaking off qubits from the system and letting them kind of disperse away. And if I take a big complicated quantum system and I pick a pretty generic state in that system and I rip off one of its qubits, then For the overwhelming majority of quantum states, then the qubit I rip off will be maximally entangled with the rest of the system, just because that's how the geometry of Hilbert space works. So our rough schematic idea as to why it is a system ought to emit blackbody radiation is it's in some big complicated generic state that keeps being mixed up, and I'm just pulling bits off that state. And unless I had very special reasons not to think the bits I'm pulling off are maximally entangled, I'd expect that they should be maximally entangled. Okay, well that's fine as far as it goes, but then that same argument would seem to suggest that the system ought to be emitting blackbody radiation indefinitely, and of course we know that can't be right. We know that after the equivalent of the page time, the particles being emitted are going to have to be maximally entangled with the earlier radiation, not with the cooling system. And there's no problem with that being the case, but it does raise the question, okay, well, in that case, why do we still in fact observe thermal radiation coming off systems after the page time? What's left of the argument that says that's what you ought to expect, rather than some other more structured sort of quantum state? And I take it there's a relatively straightforward answer. If you imagine looking at the quantum state of the system after it's emitted n qubits of radiation, it's kind of got a shape a bit like this, and it's a linear superposition of terms for each of which this argument applies. And so if you consider what the system looks like from the point, if you ignore the rest of the radiation and just look at the system, it can be treated exactly as if it were a probabilistic mixture of all of these states. I can apply this same argument for each state separately and predict that one way or another I'm going to be getting blackbody radiation out. And another way of putting that is that the emitted radiation is exactly decohering the system decaying so that it can carry on being treated as this thermal mixture of states. Now, that carries on applying even after the page time, but it's noticeable that you can mess with it. I could say, okay, I've got my quantum system. It's emitted enough photons that the system's in a maximally mixed state. I've got this argument that says its subsequent emissions should still be a thermal mixture of states that are perfectly entangled, so it should look from the point of view of an observation as if it's still emitting blackbody states. But I could, if I want to, mess with it. I could decide, right, let me find some basis for the system such that for each state in that basis, the next particle emitted will not be entangled at all, will not look like blackbody radiation. And then I'll do some unitary transformation on the system. And again, I can always find such so that the radiation modes in some given basis that I can measure are perfectly correlated with this basis. And then if I were to measure the system in the n basis, I'd subsequently predict that the next emission would be nothing like blackbody radiation. And of course, the answer to that is, well, yeah, you can do that if you like, but it's a ridiculously complicated manipulation of the field. You probably can't do it in practice. And in any case, unless you actually do it, you should still expect that the radiation emitted is basically thermal. So the mere fact that you could prevent it emitting blackbody radiation is not something that stops the description being fine in the absence of that. And here's another way of doing the same thing. Rather than thinking about the system being decohered by the radiation field, you could turn it around and ask, how does the radiation field end up decohered by the system? And you can think of the first half of the evolution of the system up to the page time as being a situation in which the radiation field is exactly decohered by the system. And so it looks as if, from the point of view of an external observer, the radiation field looks exactly like a maximally mixed state, essentially a black body state. After the page time, that can't be true. It can no longer be the case that for any given sort of fixed basis for the radiation field, states of the system are exactly orthogonal. The relative states of the system are exactly orthogonal. But it can be the case that they're really, really close to orthogonal, and that can carry on for a very long time. So in the normal story for how the sort of quantum classical transition takes place, let me skip this bit for time actually. Then we normally say something like, well, a system's quantum mechanical when interference phenomena can matter, and in that situation you can't treat a quantum system as a probabilistic mixture. We can treat a system as decohered and therefore effectively classical when, with respect to some basis, the interference is negligible, and so you can treat the system as a probabilistic mixture. And what we mean by can here is something like, well, for natural processes, those natural processes are not going to be such as to cunningly recohere the system. And any feasible interventions we could make in the system are likewise not going to cunningly interfere it. So Schrödinger's cat, for instance, is when it's decohered, It's not that an infinitely clever observer couldn't recohere it, it's that it won't recohere by itself, and nothing we can realistically and practically do to the system will recohere it. And if you apply that to the thermal case, then you find you've got a description that looks something like this. For all practical purposes, the system carries on being a probabilistic mixture of all of these branches that are coming out, where in each branch, we've got a perfectly good understanding of why the radiation emitted is thermal. The branches are not exactly orthogonal, and for that reason, the story would fail for certain unrealistic but physically possible interventions. So there are things you could do that would spoil the thermal structure, but that doesn't undermine the fact it's valid in the absence of those. So that last part was sort of suggestive hints as to what's going on here. I don't think they go much beyond the suggestive. Just to wrap up, the firewall problem, I think, is pointing to some place where the background space-time assumption to low energy quantum gravity is breaking down. We don't necessarily need to think of that as a breakdown of low energy quantum gravity itself. But in view of the fact that our normal reasons for thinking it should break down don't apply, it's helpful to look more at the breakdown of the semi-classical approximations there and look for sort of genuinely quantum mechanically interesting things going on here. And there are at least suggestive analogies there to subtleties of the quantum classical transition in more mundane thermal cases. So let me stop there.
Let's thank the speaker. And while we are answering questions, let me ask Penzi Miao, if he's around. Please, if you could get ready. Are there questions?
So a very naive question. You spoke about this topic mostly in the context of non-spinning black holes. Mm-hmm. So I'm just really broadly curious how much work has been done looking at more general types of spacetimes. And is the impression that this just makes things unruly and obviously more complicated, or there's some potential benefits to be had?
Sure. So I wouldn't claim to be an expert on the development of that, but as I understand it, the answer is that the Hawking phenomenology plays out in rotating black holes in a fairly similar way and lets the black hole lose spin as well as lose energy in ways that you can quantify. The concept that I think because the math gets a lot harder work and because the conceptual situation doesn't seem to transform very much, then most of the exploration tends to be in the Schwarzschild case. But it's always possible that that's a mistake. In particular, I think the assumption is the singularity structure of a realistic system of this kind is going to look like Schwarzschild kind, and the very different singularity structure you get in the exact Kerr solution is not going to be a reliable description of an actually stable situation of this kind. But don't ask me to justify that claim.
Let's thank the speaker again. Thank you, David. And the last talk in this session is from Pengzi Miao about black hole contribution to quasi-local mass.
Okay, I want to first thank the organizers for inviting me to participate in this nice conference. In my talk, I'm going to discuss a mathematical inequality on compact manifold with boundary, which loosely speaking can be viewed as a statement of the contribution of black hole to the quasi-local mass of the outer boundary of the manifold. My talk is planned as follows. I will first go review very quickly the setup or the formulation of the Penrose inequality. And then I will move on to the setting of the compact manifold. Oops. Sorry for that. Try to read this. Okay. All right, so for a black hole spacetime, Penrose in the early 70s proposed an inequality of the following form. And here, m denotes the mass of the space-time, and a denotes the area of the black hole. And we will be mainly focused on the initial data version of this inequality. So suppose M is an asymptotically flat Cauchy hypersurface in the spacetime. Then the initial data version of this inequality reads as follows. The left-hand side is now taken as the ADM mass of this initial data M. And the right-hand side, HM denotes the intersection of the event horizon with this initial data. Now, this inequality is still global in the sense that even though the left-hand side can be computed purely from this initial data, but the event horizon, to know the event horizon, one needs the entire space from space-time information to determine this HM. So therefore, one would like to replace this quantity by something that can be computed completely using M alone. So that leads to this rather well-known formulation of a weaker inequality. So here we have a picture. M denotes this Cauchy hypersurface. And if we take any bounded region D, we know a region D will lie inside the black hole, provided the boundary of D is weakly outer-trapped, meaning that the null expansion along outgoing geodesic is less than or equal to 0. So therefore, it's natural to consider the maximum domain of this type. So one can consider the union of all such D whose boundary is weakly outer-trapped. Then such a union lies inside the black hole. And suppose this region is not empty, and assuming we have a boundary condition at infinity that's asymptotically flat, then it can be proved that the boundary, which we denote by SM in this picture, so it's this surface inside, being the boundary of this region Tm, is actually a regular surface. It's a smooth surface satisfying theta plus equals 0. So 0 null expansion. And such a surface currently is known as MOTS. And the mathematical proof of this statement was given by Anderson and Mensker in 07, and also by Michael Igmer in 08. And moreover, by the construction, one knows that this surface S sub m is actually the outermost MOTS, which is also known as the apparent horizon of this initial data. Here, the important information is that this surface SM lies inside this horizon, event horizon. Therefore, if the Penrose inequality holds, then a consequence of the Penrose inequality would be the ADM mass of this initial data set will be bounded from below by the minimum area required of a surface that encloses the apparent horizon. It would be, once given this inequality, it's kind of curious to ask if this minimum area of surfaces, including the horizon SM, can be replaced by the actual area of the horizon, of the apparent horizon. And it's a result of Ben Knopf. He gave an explicit example, which is actually rotationally symmetric, which shows that such an inequality is not true in general if you replace this minimum area of surface enclosing the apparent horizon by the area of the horizon itself. So in general, one needs to work with this inequality with the minimum area enclosure inserted. So this inequality has a feature that both sides depends completely on the initial data. And the general case is still open. So one does not have a mathematical proof of this inequality yet. However, in the time-symmetric case, if the Cauchy hypersurface has 0-second fundamental form, then the condition that theta plus equals 0 reduces to a simple geometric condition as the mean curvature of the surface equals 0. So in this case, the apparent horizon becomes the outermost minimum surface in the manifold, and it can be proved that the minimum area enclosure due to this outermostness of the minimum surface equals the area of the apparent horizon itself. So a celebrated result in differential geometry is the so-called Riemann-Penrose inequality, which settles this inequality in the case that M is time-symmetric. And it was proved by Husken, Imanen, and by Bray separately. The paper the result was announced in late 90s, and it was published in 2002. So the Riemann-Penrose inequality states that if M is an asymptotically flat Riemannian manifold with non-negative scalar curvature, and if the boundary consists of the outermost minimum surface, then as expected, then the ADM mass is greater than or equal to the corresponding, say, the 1/2 of the area radius of the boundary, with equality holds if and only if the manifold is isometric to a spatial Schwarzschild manifold outside the horizon. Husken and Imanen proved this in the case that the black hole, the horizon is connected, and the general case was proved by Bray. All right, so by now we had a very quick review of the setup of the Penrose inequality and what's known in the time-symmetric case. Next, I'm going to move on to the main content of my talk. So first, I will state the problem. So the problem that we are interested in is the following. Given an asymptotically flat Riemannian manifold satisfying the condition in the Riemann-Penrose inequality, meaning that the scalar curvature, which is the Ricci scalar of the metric, is non-negative, and suppose the boundary consists of the outermost minimum surface in this manifold. And then, if one take a surface, which we denote by sigma, enclosing the horizon, we want to seek a physical quantity, which we denote by m, sigma, that's completely determined by the intrinsic metric gamma on the two surfaces and the mean curvature of sigma in the manifold, such that this quantity m sigma would be bounded from below by the corresponding by the 1/2 of the area radius of the boundary of M. And moreover, we want such an inequality hold becomes an equality precisely when this part of the region is isometric to a Schwarzschild region enclosing the horizon. So that's the problem that we are interested. Okay, so mathematically we can now make a definition. We can formulate the problem for an arbitrary, make a definition for an arbitrary manifold. So a compact Riemannian 3 manifold is called a body surrounding horizon, provided it has non-zero matter distribution, so the scalar curvature is non-negative. And then we assume that the boundary of this 3 manifold is a union of 2 pieces. One piece, we can call it the outer boundary, and then the other piece, we can think it as the horizon boundary. The horizon boundary is characterized by the fact that it has 0 mean curvature. Moreover, it's outermost in this 3 manifold with respect to the outer boundary, meaning that itself is a minimum surface and is not enclosed by any other closed minimum surface in omega. And our goal is, given such a compact 3 manifold, we want to establish a localized Riemannian penrose inequality on such omega. Now, to start this problem, we will focus on the case that the boundary data of the outer boundary can be compared to a surface in the spatial Schwarzschild manifold. So for this purpose, let's briefly review the spatial Schwarzschild manifold. So the spatial Schwarzschild manifold, which we denote by M, with M sub M with metric Gm, can be written as the Euclidean space with the origin deleted, equipped with the following conformally flat metric. And this is the isotropic coordinates of the Schwarzschild metric. And we have this picture, and the horizon is denoted by this minimum surface. And on this spatial Schwarzschild manifold, there is an important function which we denote by n. And using spherical symmetric coordinates r, this n is the square root of 1 minus 2m over r. And we call this function the static potential because the warped spacetime metric is the Schwarzschild spacetime metric. And we are going to use this n later. All right, so go back to our question. So given a compact body, given a body surrounding horizon, we are going to make a rather strong assumption, which I will come back to it later to give some comment. Suppose this outer boundary of omega is isometric to a suitable surface in some Schwarzschild manifold enclosing the horizon. And here, suitable means we want this surface, the image of this embedding, to be convex. And moreover, there is a technical assumption on the Ricci curvature along the normal direction. We want the Ricci curvature of the Schwarzschild manifold along the normal direction to be non-positive. That's a technical assumption. So in this setting, one can prove the following inequality. So with this embedding x, one can pull back the static potential n. Recall that the static potential n is a function defined on the spatial Schwarzschild manifold. One can pull back n to the boundary sigma, which we still denote by n itself. So on this outer boundary of this physical manifold, one considers this weighted integral of n with the mean curvature normalized by 1 over 8 pi plus the 1/2 radius of this horizon boundary. And this sum can be shown to be less than or equal to the corresponding quantity in the Schwarzschild manifold. And here sigma m sub h denotes the Schwarzschild horizon. And moreover, in this inequality, the equality holds precisely when this physical manifold is isometric to the region bounded by sigma and the Schwarzschild horizon in the target. Okay, let me give some comment regarding this assumption on the isometric embedding. Before I move on to that part, let me first state an equivalent form of the previous inequality. Now, we know the area of the Schwarzschild horizon is the 1/2 area radius of the Schwarzschild horizon is precisely m, the parameter m, which is the mass of this target space. So therefore, we replace this term by m. One can rewrite this inequality as inequality 6. So in 6, we have the mass parameter of the target space plus this weighted integral dominates the 1/2 radius of the horizon boundary of this physical manifold. So in particular, if we denote this expression by m sigma omega m, then this quantity satisfies the property that we ask in the beginning. We will give more comment on this quantity after we give remark on the isometric embedding. Okay, so regarding the assumption on the isometric embedding, Lu and so my collaborator, Suyuan Lu, and I show that in an asymptotically flat manifold, if you look at a coordinate sphere near infinity, such a coordinate sphere can always be isometrically embedded into a Schwarzschild manifold, provided the coordinate radius is large. Moreover, this embedding can be arranged in a way that the corresponding expression on the left side of our inequality approaches to the ADM mass. So therefore, this fact, together with the fact that our proof of the inequality 6 makes use of the remaining Penrose inequality, shows that 6 is equivalent to the remaining Penrose inequality. So going back to this inequality 5 or 6, so if one views this as a pure result in Riemannian geometry, and if one can prove it not using Penrose inequality, then this would indicate a different proof of the Riemannian Penrose inequality. And again, this is a result with my collaborator, Suyuan Lu. All right, now, as I said, I would like to give some comments on this expression in a setting that, assuming this outer boundary isometrically sits in the Schwarzschild spacetime. So my first comment is, if the mass parameter m equals 0, in other words, if this reference space is the Euclidean space, then this expression reduced to 0 plus the corresponding integral in which n is 1. And that's known as the Brown-York quasi-local mass of sigma. And in that case, existence of isometric embedding of surfaces with positive Gauss curvature into the Euclidean space was proved by Nirenberg in 53 and also by Pogorelov in 52. And the positivity of the Brown-York mass was proved by Shitan in 2002. So that's the case where this parameter m equals 0. Now, if m is not 0, the integral in the expression m, sigma omega m, is related to the Wang-Yao quasi-local mass in the following sense. So more precisely, again, given this setting, recently Wang-Yao, there is a notion of Wang-Yao quasi-local energy with reference to a static spacetime. In this case, the static spacetime is the Schwarzschild with respect to a given embedding into the target spacetime. Now, in our setting, in the setting we are interested, this omega g is a Riemannian manifold. Therefore, it should be seen as a domain in the time-symmetric data. So thus, it's natural to consider embedding into the spatial piece of the Schwarzschild spacetime. Given such embedding, the Wang-Yao quasi-local mass, the Wang-Yao quasi-local energy numerically agrees with this integral on the left-hand side. So therefore, using this notation, the inequality 6 shows that the Wang-Yao quasi-local energy with respect to this embedding into the spatial Schwarzschild manifold has a lower bound, which is given by the 1/2 of the black hole radius minus m, which is a target, which is the mass of the reference space. Coming back to this inequality, the expression on this left-hand side so far not only depends on our physical manifold, but also depends on the target space M, Schwarzschild manifold with mass M, and also the given isometric embedding X. So therefore, if one go ahead to minimize overall isometric embedding and minimize over the reference space, the target space, then one would get an inequality that's determined completely by the triple sigma gamma h. And to end this talk, we are going to use an example to illustrate this minimization procedure. And the example we have is a case where the outer boundary of this body is the simplest case, is a round sphere. So here I want to remark that even though we assume the intrinsic metric to be the simplest case, the mean curvature of this outer boundary can be arbitrary. We have no assumption, we impose no assumption of the mean curvature function. And the inner black hole boundary also is allowed to be arbitrary. So in this case, because the outer boundary intrinsically is a round sphere, then naturally one just considers the obvious isometric embedding, which places this outer boundary into a Schwarzschild manifold as a rotationally symmetric sphere. And we know there are lots of choices of such a reference space. For any parameter m, from 0 to 1/2 radius of this outer boundary sigma, one can consider this picture, and then one can do a calculation. In this case, this static potential is a constant on the surface. So therefore, one can carry out this calculation, and it's a quadratic function of the total mean curvature h. So minimizing this functional over the parameter m, one arrives at an expression which is given here. So 1/2 radius of the area of sigma times 1 minus 1/16 pi, divided by the area times the square of the L1 norm of h. So this is the last slide. So therefore, for this special case where the outer boundary of the omega is a round sphere, our result shows that this quantity, which we denote by star, is bounded from below by 1/2 of the horizon area. Moreover, equality holds if and only if this configuration is precisely a region bounded by a rotationally symmetric sphere and the horizon in a Schwarzschild manifold. And two comments. The first one is, note the similarity between this expression m star with the Hawking quasi-local mass. The only difference is in Hawking's mass, one has this L2 integral of h. And in the quantity we have on the left-hand side, we replace it by the square of the H1, of the L1 of h. And therefore, by Holder inequality, this m star is larger than Hawking mass. On the other hand, it is not known if the Hawking mass has the property that it's always bounded by the horizon area in such configuration. So that's one remark. And another remark is more interesting to me. This value m star being self of the infimum of the functional we try to minimize. Okay. So we minimize this function over m, and we get a value m star. And that infimum of the functional numerically turns out to be the optimum parameter m that achieves this infimum. So here we have a functional. If you minimize the functional, you get a number, and that number turns out to be where this functional is minimized. And in that sense, so this suggests that an optimal reference. Okay? So if we go back to the to this in picture, one would ask, you have so many choices of a reference space. Which one would be the optimal one? And here the answer is the optimal reference can be or may be obtained by minimizing the corresponding functional over all reference spaces. And I'll stop here. Thank you.
Our questions.
Thank you. I would like just to ask you the role of angular momentum. So for a given mass, the Kerr black hole has a smaller area than the Schwarzschild black hole. And so what about these bounds? Are they less sharp, or what is the role?
Well, yeah, so far all the result is on the remaining case, which meaning the time symmetric, so no angular momentum. And there is not a general, so far, as far as I know, there is no general proved inequality in the general case, but assuming axis symmetric case, there are results on the axis symmetric Penrose inequality with non-zero angular momentum, but I'm not an expert on that area. So my expectation is to get the quasi-local analog, one would need to first go. It's kind of a strange scenario to get the result on compact piece. So what one does so far is indeed first go to the non-compact piece to prove the full Penrose inequality for asymptotically flat manifold, and then apply that result back to the compact piece. So that's how we prove this case. So therefore, going back to your question, to understand the quasi-local phenomenon in that case, still one would need to first understand the non-compact piece first.
Any more questions or comments? Well, if not, let's thank the speaker again. And thank you for attending this first session. Now 30 minutes for coffee.
Okay, so we're going to begin our final session this morning, the final day of our third annual BHI conference. And our first speaker is Shahar Hadar. He's a postdoc in the physics department here at Harvard. He's going to be speaking to us about back reaction in near-extremal black holes.
Okay, thanks very much, and thanks very much for the opportunity to speak in this wonderful conference. Proving black hole stability is a long-standing problem in mathematical general relativity. There's much recent progress on the subject. The ultimate goal will be proving the full nonlinear stability of Kerr or Kerr-Newman under gravitational perturbations. We're still not there, but I am told we're getting closer and closer. And the basic quantity which is studied in these problems is whether and how perturbations decay at late times on black holes, whether these solutions decay to stationary black holes at late times. Specifically, one looks at so this is a Penrose diagram and the compactified diagram of space-time in which light propagates in 45-degree angles. So this line here stands for the horizon, and perturbations need to decay also on the horizon at late times, which will be our focus today. So on the horizon at late times is this part of the Penrose diagram. And for non-extremal black holes, it's a well-known fact that perturbations decay exponentially, like e to the minus kappa v, where kappa is the surface gravity of the black hole. But this already shows that, and this is called the redshift effect, but we can see from this formula that the redshift effect will be problematic when kappa goes to 0, when we go to extremality. So we need some other ways to analyze this problem. So a slide about extremal black holes. So extremal black holes are a zero temperature or surface gravity black holes with degenerate horizons, and they saturate bounds on charges and angular momentum. They have generically an enhanced symmetry group in their near horizon region, which will be I'll talk about later. And they play a very important role theoretically in string theory and holography. And it's a real possibility that near extremal black holes, the ones that are rapidly rotating Kerr black holes, actually exist up in the sky. So that's why they're interesting to study. And back to the black hole stability problem. So we said that the extremal problem needs to be analyzed in a different approach. And Stefanos Aritakis, who was here in the audience, talked about this also on Monday. In his PhD, analyzed this problem very closely and found a very surprising result that extremal black holes display both stable and unstable properties. So the stable property is that the field linearized perturbations on extremal black hole spacetimes do decay at late times, but their derivatives in general don't need to decay. And as you take higher and higher derivatives, the behavior of these quantities actually becomes worse and worse. They actually blow up on the horizon at late times. So this is an example of what happens to spherically symmetric perturbations of a massless neutral scalar field. As you take k radial derivatives, so derivatives across the event horizon, and look at this quantity at late times, at very large v, which is the ingoing Eddington-Finkelstein coordinate along the horizon. And this quantity behaves like v to the k minus 1 for massless perturbations to extremal right and Nordstrom spacetimes. So when k equals 0, we're not taking any derivative. This spherically symmetric field just decays at late times. But if we take one derivative, this already does not decay at late times. It goes to a constant. And if we take more and more derivatives, this will blow up polynomially. And a very related fact that Stefanos also found is that there is an infinite number of conserved quantities on the horizon, so-called Aritakis constants or charges. Okay, and this is related to the fact that some things don't decay at late times on the horizon. And many other people studied various generalizations of this, and I can't list them all here. But it was found that this is really a generic feature of various kinds of perturbations to various kinds of extremal black holes that
if you take k derivative across the horizon of some general perturbation field phi, this will behave like v to the k plus delta, where delta is some constant which depends only on the type of perturbation and type of extremal black hole, and k is the number of derivatives. So you see that, for example, for spherically symmetric perturbations of a massless scalar field on extremal Bryson-Nordstrom, delta equals -1. That can be various other things. It's always negative, so the field always decays for 0 derivatives. Okay, so the question is, physically, what's going on there? How can we measure this effect in any way? And also, what's the endpoint of this instability? What's the final state of the black hole? Relatedly, one can ask, okay, derivatives are growing at late times, and more derivatives are growing worse and worse. So one can worry that if you add higher derivative corrections to your action, these corrections can actually dominate the action at late times. And this is a breakdown of effective field theory. So this is a question I studied together with Harvey Rial, and we found actually that you can't build any curvature invariant that from the field or the metric that blows up at late times. So we see this as evidence that effective field theory is preserved actually at late times, but it's by no means a full proof. Another interesting paper by Murata, Rial, and Tanahashi studied the back-reacted case numerically. So the question is, okay, we're studying linearized perturbations on some background, and these linearized perturbations are growing and growing. So it kind of seems that we need to include back reaction in the story, at least in the places where the perturbations are very large. And so these people studied this problem, and they found that for generic initial data, the final state of this perturbed extremal black hole is a slightly non-extremal black hole. But you can choose some fine-tuned initial data, so you can have an eternally evolving extremal black hole. But for this, you need to do an extra fine-tuning of the initial data. So my final goal today is to study the back-reacted case, but with analytical methods. So these are the 2 points that I want you to take away from this talk. One is this late-time behavior, including the Aretakis instability, can be understood from a symmetry perspective, a near-horizon symmetry perspective. And the second point is that this understanding allows us to solve analytically for the back-reacted solution of the field plus the geometry. Okay, so the system we're going to study is, again, a massless neutral scalar field propagating on the extremal Reissner-Nordstrom space-time. To base the wave equation on that space-time. And this is the metric of Reissner-Nordstrom. So M is the mass and Q is the charge of the space-time. And I will focus on the case where Q is very close to M. So this parameter kappa hat is how close I am to extremality, and it will be much smaller than 1. It's exactly 0 at extremality when Q equals M. Okay, so one thing that's needed to understand about these space-times is that actually these static Reissner-Nordstrom coordinates in the near extremal and extremal limits, they do not resolve the near-horizon geometry correctly. So if one takes, so they actually miss a whole chunk of space-time that has infinite volume, and it's also a solution of the Einstein equations in its own right, and that's the near-horizon geometry. Okay, so in order to resolve this near-horizon geometry, one can choose a coordinate system that zooms in on that geometry and resolves it. And this is done by defining this one-parameter family of coordinate transformation, which is parameterized by this epsilon, which we will later take to 0. And for now, we will take an exactly extremal black hole, so kappa hat equals 0. And why is this a zoom in on the near-horizon region? Because you can see that this big R, which will be the big R and big T will be the near-horizon coordinates. So big R assumes only finite values when R hat is very close to M of the order of epsilon. So when we do that procedure, this zoom in on the near-horizon region, we find that the near-horizon region is actually you can think of it in a cartoon as an infinitely extended throat, which has this geometry, ADS2 times S2, or the Robinson-Bertotti universe. And it's glued along some boundary to the external extremal Bryson-Nordstrom spacetime. So you can think of the spacetime as splitting into two parts, the far region and the near region. And the near region is described by this geometry, which has an enhanced isometry group. So it enhances the R times SO3 isometries of Bryson-Nordstrom, so time translations and rotations on the sphere, to a conformal group SL2R with 3 generators instead of 1, times, again, the SO3. We're not touching the sphere. Okay, but turns out that's not the end of the story, because there's other ways to take this near horizon geometry. One can also assume that we're only near extremality, so we'll take the near extremality parameter to be of order epsilon with some proportionality coefficient kappa, and define the new coordinates in the similar way. We call them small r and small t. And when we do that and take the epsilon goes to 0 limit, we get a different metric, which we call the near ADS2 metric, times S2. Okay, so the sphere we're not touching, but this ADS2 part becomes near ADS2. This small n stands for near ADS2, and you see this parameter we defined pops up in the metric. So what's going on? What's the real description of the geometry? Is it near ADS2 or ADS2? The story is that locally these geometries are the same. They're actually diffeomorphic, but they cover different patches of the full space-time. So this near ADS2 or Rindler patch covers a patch like this in the maximally analytically extended near horizon geometry, which is a strip with 2 time-like boundaries. And the Poincare coordinates, which were the first one I showed, the one I called the ADS2 metric, cover this type of patch, which touches the other boundary. And it's a different kind of, globally different kind of geometry, but locally, they're all ADS2. They're all diffeomorphic to each other locally. And this is just to show what I'm doing when I take this near horizon geometry. I'm focusing on this red strip of the, this red strip here is this red strip here. Okay, in the full geometry. Okay, to get a little bit of feeling for what this SL2R, how this SL2R operates on the near horizon geometry, we have this diagram here. So we have Poincare time translations in the time according to these Poincare coordinates, which just translate us kind of in a parallel direction to this red line, which is a fixed radius trajectory in ADS2. Okay, so they kind of go like this. I can try to, oops. So these are translations along Poincare time. And we have dilatations that kind of take this trajectory down and up in R. This is how dilatations work. And we have global time translations, which kind of take this whole Poincare patch and shift it up and down the maximally extended geometry. So this is how these 3 symmetry transformations can be thought of. And on top of that, we have a slightly more generalized type of symmetry, which is cutting these Poincare patches into smaller Rindler patches. And all these kinds of patches can be thought as near horizon geometries of some near extremal Bryson-Nordstrom geometry. Okay. Fine, we have all these symmetries now as tools, but what do we want to do with them? So we want to use this as a tool to generate new solutions. Okay, why does this work? If we have a solution of the wave equation, box phi equals 0, we can define a new solution, which is just the action of the symmetry on that old solution. Okay, and now this new solution is also a solution to the wave equation because the symmetry commutes with the wave equation operator. Okay, that's the whole story. But of course, psi and phi here are different solutions. Okay, it's like taking a solution to the Laplace equation on a sphere, which is like a spherical harmonic, and rotating the sphere. So we get a different spherical harmonic, but it's also guaranteed to be a solution automatically because of the spherical symmetry of the problem, not of the solution. Great. So now let's use all these tools to find out what's the late time behavior just from the symmetry. So if we look at the Poincare patch and we put some initial data on this dashed line here, for example, and some boundary condition on the boundary. Then we find, let's put just Dirichlet boundary conditions, which tell us that the field needs to vanish on the boundary for simplicity, but this can be relaxed a bit to some extent. So the field will behave near the boundary as some smooth function of the time, because it's just some time in some generic time on the boundary. I call it T infinity here. You'll see in a second why I'm calling it that. And there's a fall-off with R, because we're demanding the field to decay near the boundary. And let's call this power of the fall-off delta minus. Fine. So now we can perform the coordinate transformation that corresponds to a shift of global time in this ADS2 strip. Okay, this is given by this coordinate transformation between the coordinates without tilde, which describe this upper patch, and coordinates with tilde that describe this lower patch. Okay, and then I can move also to ingoing Eddington-Finkelstein coordinate. Instead of T tilde, I'm moving to V tilde, because I want to study the horizon at late times. And then I'm just using this coordinate transformation of the expression for the field. Okay, and I'm finding that the field behaves on the horizon of that patch at late times like V tilde to the delta minus times some smooth function of R tilde times V tilde, where R tilde stands for the horizon of this lower patch, and V tilde is this ingoing Eddington-Finkelstein coordinate along the horizon of the lower patch. So from this, I can see that if I take k derivatives with respect to R tilde and plug R tilde equals 0, which means I'm exactly on the horizon, then I get exactly the behavior that Stefanos found, that Stefanos proved. But I'm getting that directly from a symmetry argument. Okay, I don't need to solve any more equations. Okay, and this can be done also for a near extremal, to understand the near extremal behavior. So I'm again starting from a patch like that. The solution is some smooth function of t times r to the delta minus. And then I can use a mapping between the Poincare patch and a Rindler patch, or a near ADS2 patch, which is given by this coordinate transformation. And then I'm just I'll save you some of the equations. What you get, basically, if you expand near the boundary, you get a sum over decaying exponentials with some amplitudes, and the coefficients of decay in these exponentials are exactly the quasi-normal modes of these black holes. Okay, these correspond to the weakly decaying quasi-normal modes. So this gives you exactly the quasi-normal mode decay directly from a symmetry argument. You don't need to solve any more equations. And of course, you get an expression also for the amplitudes, which depends on the behavior of the field in the original patch. And also you can find also from the symmetry argument the transient instability behavior found by Grala and Zimmerman, also from the symmetry argument, just by analyzing the behavior on the future horizon of this near ADS2 patch at early times, intermediate times, and late times. Great, so I think, so that was the first point. The late time behavior follows directly from the symmetry. Now I want to go to the back reaction issue. So we talked about that numerical paper it was a beautiful paper by Murata, Real, and Tanahashi. And this is, okay, so they argue that back reaction must be accounted for because we have linearized perturbations that are blowing up sometimes at some point in the space-time. And this is also a well-known fact from ADS2 physics, that ADS2 does not admit finite energy excitations. This was understood in the string theory community. So, and these facts are in fact related. So in order to understand back-reacted ADS2 physics, you can't be in pure ADS2, you have to work in near ADS2. And this is why we turn to the Jakiv-Teitelbaum gravity, which is a model for the near horizon physics of spherically symmetric perturbations to maximally charged black holes. And this has got a lot of attention recently in the context of the search for a duality between a two-dimensional gravity theory and 0 plus 1 dimensional field theory. Okay, so in the context of holography between 1 and 2 dimensions. Okay, this is the theory, Jakiv-Teitelbaum gravity. It's a two-dimensional gravity theory. So it has one bulk gravitational term. So of course, we can't have pure gravity in 2 dimensions because it's trivial. So we'll need to add some dilaton field, which is part of the gravitational action, which is coupled to the Ricci scalar. And this dilaton field stands for the volume of the transverse sphere along this throat. Okay, so this is what this phi stands for. And it's coupled to the Ricci scalar of the 2-dimensional metric. So this is the bulk gravitational part. There's a Gibbons-Hawking term we add on the boundary, since we have to cut off the boundary at some point. And we have a matter action. Okay, which that's not universal. We can decide to put on any matter that we want, but we will put the simplest case of neutral massless scalar field propagating on this 2-dimensional geometry. And we will parameterize this boundary by T boundary of U proper time on the boundary and R boundary of U. But there's actually a relation between T boundary and R boundary, so we'll only need to focus on T boundary, essentially. Okay? So this is the picture. Sorry, I didn't say something something important. I didn't say something important. So actually, one can get rid of this bulk gravitational term by integrating out the dilaton field, big phi, because it's an auxiliary field. It appears in the action with no derivatives. So its equation of motion just tells us that R equals -2, and then we get locally an ADS2 geometry. So we're left, forget about this term. We're left only with these 2 terms, a boundary term, which encodes all the gravitational dynamics, and a matter term, which is basically everything we want to put in there. So it becomes a very, very simple theory. The solutions are always locally ADS2, and there's a boundary which has some trajectory, which is the only degree of freedom of the gravitational sector. Okay, so this is the picture. In the bulk, we have just locally ADS2. It's cut by some boundary along some trajectory, which is the gravitational degree of freedom. And we have, in addition, we have a scalar field propagating on that geometry. And the equation of motion, so we're doing classical physics here. So the equation of motion which determines the evolution is this equation down here. So this is just an integration constant, which is the energy corresponding to this boundary. And we have a Schwarzian derivative of the trajectory of the boundary. This is this curly brackets here. This is the definition of the Schwarzian derivative. Okay? And we have another term which depends on the stress energy tensor, in particular this pressure of the matter, of the fields we're putting in. So there's fields we're putting in particular their value on the boundary, the Schwarzian derivative of the boundary trajectory, and some constant on the left-hand side. So the picture is that we have fields propagating on the boundary, bouncing off this boundary, and when they bounce off the boundary, they interact with it and kind of makes it change its trajectory a little bit. Okay, so the only interaction, the only thing we need to take into account to solve the back-reacted problem is this interaction between the boundary and the fields bouncing off it. Okay, and this is how we get the solution. So imagine that at some advanced time v equals 0, we put some initial data surface, or we can also throw in a pulse of matter from afar. So this interaction with the boundary will make it change its trajectory. Instead of being on this dotted green line now, it will follow this blue line. Okay, it will meet the boundary of global ADS2 in an earlier time. We'll call that now T infinity. And now the back-reacted event horizon will be this red line here. Okay, so that's all we need to compute. And that's basically amounts to solving these 2 coupled equations, the wave equation for the field on the bulk, and the Schwarzian equation for the gravitational degree of freedom. Okay, and when we get that, we solve the full problem. And it's very easy because the reason why it's easy is that really for the scalar field, you don't need to solve any coupled equations. You just need to solve the wave equation on a fixed ADS background. That's what makes this formulation of the problem very simple. So I'll flash in a second the full solution, but maybe it's less illuminating. So this point is maybe the most illuminating. You find that on the back-reacted event horizon, you find quasi-normal modes which are now shifted because of the back reaction. they look like the original quasi-normal modes, but with a shifted surface gravity. Instead of kappa hat, it will be kappa hat prime, which is kappa hat plus some amplitude squared of the field we threw in, which means that exactly this takes into account the fact that the final black hole just absorbed some energy, and now its deviation from extremality is a little bit different. So the quasi-normal modes have changed. And we can get all that analytically using this approach. And this is the full solution. So we can get basically the solution here everywhere on the boundary, on the horizon, the transient part, whatever. It's just given by this expression, where this RB is given by this expression, and U and V, which are advanced and retarded coordinates on the Poincare patch, are given by this expression. So, I mean, this is just to show that the full solution exists and can be analyzed. Great, so that's the points I wanted to convey. The first point, the late time behavior. So understanding the symmetry properties of the near horizon region shed some light on this surprising effect of horizon instabilities in extremal black holes. And the second point is that this allows us to solve some model of the back-reacted case analytically. Thank you.
Questions for Shahar?
Two quick questions. The first is, so I didn't understand how you impose boundary conditions if you're using just the near horizon geometry. How sure are you that you're capturing well spatial infinity, for instance? And the second is, so I would expect that the instability of extremal geometries tells us that no black hole is going there. So can you comment on that?
That no
black hole in the universe will get to the extremal limit.
Right.
Also for that reason.
Yeah, okay, let me start from the second one. I think that, I mean, realistically, we should, I mean, if we're thinking about studying something realistic and looking for signatures, then we definitely need to look for near extremal black holes, not for it. I mean, there's a fine-tuning, on top of the fine-tuning of the angular momentum, you need to also to fine-tune the initial data. So it doesn't seem reasonable. It doesn't seem realistic, I would say. The first question about the boundary conditions, well, I mean, I was skipping this pretty quickly, but wait, oh. So actually the boundary conditions that matter for the late time behavior here are only what happens exactly at that point, t equals t infinity. So you need to assume something about the derivatives at that point. And it's by no means a rigorous analysis, but I think these conditions are guaranteed by the decay of fields outside the black hole, by results we know about the decay of fields.
So you mentioned that the near ADS2 was dual to some 0 plus 1, the field theory. I was wondering if you could elaborate on that. I was wondering if you could elaborate on that a little bit more, on if you could, if there are any applications, say to what you talked about, just say some SYK model.
Right. Yeah, so I think it will be nice to understand what this means from the SYK point of view. I mean, my intuition says that this is the fact that if you have a quantum mechanical system at some zero temperature, and you do some perturbation to it with not, I mean, this perturbation doesn't have zero energy, maybe slightly non-zero energy, then, okay, there will be some, I don't know, scrambling in the system, and eventually the system will thermalize, but with a very small temperature, which is exactly the energy that you put in. So this is kind of, yeah, but it would be nice to understand this in more detail from the SYK point of view, I think.
Further questions for Shahar? Okay, if not, let's thank him.
This is working, right? Yep. That's for you. Yes, I think so.
Okay, so our second speaker is Patricia Palacios. She's an assistant professor in the philosophy department at University of Salzburg, and she's speaking to us about the universality of Hawking radiation.
So thank you. So first of all, thank you for the invitation. It's really a honor for me as a philosopher to be here, invited to speak at this great conference on black holes. So this is a joint paper that I have with Sean Grip from the University of Groningen and Karim Thibault from the University of Bristol. You can find a draft version of this paper on the archive. It's in both the physics archive and also the philosophy of science archive, so you can choose. So let's start. As you all know, in 1974 and 1975, Hawking famously predicted that if one considered quantum effects in the treatment of black holes, then we will arrive at the conclusion that black holes are not black after all, but that they emit thermal radiation. So without going into details of this thermal radiation, because I assume you are all familiar with that, one can just basically describe this Hawking radiation as the fact that there will be a flux of out particles at future null infinity, even if there is no flux of in particles from past null infinity. So for Hawking, this Hawking radiation was associated with a particular temperature here that was proportional to this K, that was the surface gravity. Now, the mechanisms behind this Hawking radiation are still unknown. There have been some proposals, but there is no consensus in the physics literature about what actually produces this radiation. But one can assume that if we want this Hawking radiation to be robust under the physics of the collapse, we would need at least three conditions. The first, we would need exponential redshift for free-falling modes as they approach or they are far away from the horizon. They approach approximately this infinite time, time-like infinity. One needs to assume regularity conditions that guarantee that this Hawking effect will be will be robust under UV perturbations, and one needs to assume an event horizon. So, interestingly, these conditions that assure that Hawking radiation is robust under the physics of the collapse are the same conditions that motivate us to cast doubt on the existence of Hawking radiation. And the reason is that because if we trace back this exponential redshift, we can conclude that the modes that are found for late time observers were caused by energies that were far beyond the Planckian energy. So this is called the trans-Planckian problem. And this trans-Planckian problem is very important because not only it's hard to deal with high energies in physics, but also because if this Hawking radiation depends on trans-Planckian energies, that will go beyond the semi-classical approximation. So this semi-classical framework actually breaks down for energies that are far beyond the Planckian energy. So in Unruh's term, if one examines Hawking's original calculation, there are some severe problems with his derivation. While mathematically impeccable, they are nonsense physically. Frequencies which are needed to explain the radiation produced even 1 second after a solar mass black hole forms correspond to energies which are e to the 10 to the 5 times the energy of the whole universe, right? So what can we do? There have been proposals to try to solve this trans-Planckian problem. For us, the proposals that are more convincing or more promising are proposals that try to show that Hawking radiation is both robust and universal. And here is where we think that we as philosophers can contribute to the physics literature, in particular in the distinction of terms. So there is an interesting distinction that one can make between robustness and universality, terms that generally are conflated in physics and philosophy. So one can define robustness as insensitivity of some behavior to variation of the microphysical details that characterize the particular token of the type of system being considered. Particular token here is a particular instance of the type of system being considered. And universality here is insensitivity of some behavior to changes in the macroscopic details that characterize the type of systems that are considered. So in other words, in case this is too confusing, robustness here means that a particular behavior that we observe in a particular type of system is insensitive to microscopic variation, for example, to microscopic details. Universality here means that we can find exactly the same behavior in different types of systems. So for us, what one would need to solve Trans-Planckian problems are arguments that prove both universality of Hawking radiation and also robustness of Hawking radiation. Why is that? Because one would like to show that there is insensitivity of the effect to different possible ultraviolet physics for a given type of black holes. So one would like to prove that the Hawking radiation found in a particular type of black hole doesn't depend on quantum gravity effects that are caused by this high energy physics. On the other hand, one would like to extrapolate these results of robustness to different types of black holes. So one would like to prove also universality. It is the same effect, it is the same Hawking effect that is found in different types of black holes. So different universality arguments have been offered in the context of Hawking radiation. And the question is, how can we assess the strength of these universality arguments? Or in other words, how can we assess whether these universality arguments actually prove that the Hawking effect is robust and universal so that we can solve the Trans-Planckian problem? So to do that, we follow the following strategy. We took as a starting point the successful Wilsonian framework for universality. And from there, we elaborate a general framework based on 6 qualities that allowed us to assess the universality arguments given in the context of Hawking radiation. So these 6 qualities or 6 properties that characterize Wilsonian universality arguments are the following: robustness, physical plausibility, degree of universality, empirical support, and most importantly, integration, which means that the arguments for robustness and universality are consistent. To anticipate the conclusion, we arrive at the conclusion that neither of the available universality arguments for Hawking radiation measure up to their Wilsonian counterparts. So there's no available universality argument for Hawking radiation that can show to be strong enough in these 6 qualities. For us also, this failure of integration that I will explain later in this talk is the most serious problem. So now, this is the plan for the rest of the talk. I will be very brief in this item, so don't worry. I think I will have enough time to go through all of them. So the strategy of doing that will be to skip many technical details, so we can discuss about technical details in the Q&A, or you can read the paper. But for the purpose of this talk, I will just stay on the more general level. So let us remind what Wilsonian universality arguments are. And why do we start from these arguments in our analysis? So the most prototypical case of universal behavior in physics is phase transitions in condensed matter physics, in particular continuous phase transition. One can actually observe in laboratory that different phase transitions that characterize systems as diverse as fluids or ferromagnet behave exactly the same way near the transition, in the same that the power laws that describe that behavior are exactly the same, being the critical exponents being also the same. Here is a scheme for temperature versus density for 8 different gases, and you can see how their relationships coincide. So one of the biggest puzzles of the 20th century was trying to give an explanation of this universal behavior, like why is it that we observed this common behavior among disparate systems. And one of the problems was the Landau's theory for mean field theory that was firstly used to try to explain this universality, predicted that close to the phase transition there would be infrared singularities, which could imply that fluctuations govern the behavior, and therefore this whole framework of Landau would break down. Now, one of the greatest achievements also in the physics of the 20th century was try to give an explanation of this universal behavior, and that was given in terms of renormalization groups elaborated by Wilson, Fisher, and Kadanoff. I will not go into the technical details of renormalization group because, as you know, they're very complicated, but the idea here is that one defines a transformation that successively coarse grains the system, so that we analyze how the coupling constant that describe the system change under this coarse graining transformation. By analyzing the behavior of coupling constant, one can distinguish between three classes of coupling constants: relevant coupling constants, which increase and tend to infinity as we apply this transformation; irrelevant coupling constants that tend to disappear when we apply this coarse graining transformation; and marginal coupling constant, which takes ultimately constant values when we apply this transformation infinitely many times. Now, the disappearance of irrelevant couplings and the existence of non-trivial infrared fixed point is precisely what resolves the problem of infrared singularities in the renormalization group approach. And moreover, it is the same framework that can prove that critical phenomena are both robust and universal. They are robust because one can, by getting rid of this irrelevant coupling constant, one can show that the behavior of phase transition in a particular system is insensitive towards these microscopic details. And on the other hand, by showing that these different systems flow to the same fixed point, one can explain universality, which is the fact that different systems, different types of systems, display the same behavior, which is the phase transition. So on this, taking this as a prototypical case, we made a general framework based on the qualities that I mentioned before, and one can see that Wilsonian renormalization arguments score very well in all these qualities. They prove to be robust. Most of the coupling constants are shown to be relevant, actually. They have a high degree of universality. One can show, for example, that the Ising model, the ferromagnet, and the liquid gas are in the same universality class. They are physically plausible, which means that we can de-idealize the system. We can justify the idealizations that we made in our models. And one of the reasons why these arguments are physically plausible is because one can show that idealized model, like the Ising model, is in the same universality class as real systems, so we can justify the use of this Ising model. They are highly comprehensive. They refer to almost all observables. They have empirical support. One can calculate accurate values of the critical exponents in the neighborhood of fixed points. And they are highly integrated because the framework that we give for universality and robustness is the same. So this is the framework that we use to evaluate universality arguments given in the context of Hawking radiation. Let us briefly analyze the first set of arguments. These are arguments that use the equivalence principle. So these arguments use Einstein equivalent principle between acceleration and gravitation. And by assuming that principle, they identify the Hawking radiation detected by stationary observers outside the event horizon with this Unruh radiation detected by accelerated Rindler observers in a Minkowski space. Then, since there are Wilsonian-style universality arguments for Unruh radiation, using this identification, they extrapolate the robustness that is founded in Unruh radiation to the case of Hawking radiation. So we evaluate these arguments, and this is the conclusion that we obtained in comparison to the Wilsonian arguments. As you see, they don't do very well in almost all the properties that characterize Wilsonian arguments. In particular, even if these arguments that use the equivalence principle are very high in universality, they are applicable to Rindle and Schwarzschild spacetime, and they can be extended to various other types of black holes, astrophysical black holes. They can also be extended to analog models, maybe. They have this high degree of universality at the price of decreasing the degree of robustness. In particular, these thermal properties of the Unruh spectrum are invariant only under arbitrary Lorentz invariant modifications, but they are not insensitive to non-Lorentz invariant cutoff, and also to a variety of quantum gravity effects. Moreover, and more complicatedly, these arguments apply only to observers that are close to the horizon. And if we move the observer far away to the horizon, then the equivalence doesn't hold anymore. So that also affects the robustness of these kind of arguments. Physical plausibility is very low for the same reason. This implies that we extrapolate the physics near to the horizon to the physics for an observer far away from the horizon. Comprehensiveness is very low. They only contain one member, that is temperature. Empirical support is absolutely lacking for these kind of arguments. And integration, which is the consistency between robustness and universality arguments, is also very low. Actually, the theoretical basis for universality is in tension with the theoretical basis for robustness. One can see that in order to have universality, we have to sacrifice robustness. So the framework for robustness and universality is inconsistent. Let us look now briefly to the second argument based on horizon symmetries. As I said, I will not go into the details. You can find these details in our paper. But here, the basic assumption is that Goldstone bosons that are created in the broken conformal symmetry of the horizon geometry are interpreted as Hawking fluxes. So here, the argument goes as follows. The near-horizon Klein-Gordon modes are written as representations of Virasoro algebra, whose quantization is well known. Then in 1+1 dimension, there is a broken conformal symmetry of the horizon geometry, and this quantum mechanically broken conformal symmetry can be seen to lead to the generation of Goldstone bosons that must be present to cancel the anomaly. And then since the state counting of the Goldstone bosons generated by the anomaly can be found exactly to reproduce the Hawking entropy, we made the identification of Goldstone bosons with Hawking flux. And then since Goldstone bosons are remarkably robust, they are invariant under a wide range of possible microphysics, then we imply that Hawking radiation is also robust. So here what we want is to prove the robustness of Hawking radiation, but then again, the price to pay for that robustness is universality, is decreasing the degree of universality in this framework. So these frameworks are highly robust. Actually, any UV modification that preserves the symmetries will have the same spectrum of Goldstone bosons. But universality here is very low, in particular because we restrict the type of black holes in which we can apply these arguments. For example, one assumes here that there is no back reaction and there is no evaporation effects, which is a highly idealized assumption. So it's questionable whether these arguments apply even to non-stationary and evaporating black holes. So they are very robust, fairly robust, but again, they apply to a very restricted type of black holes. Physical plausibility here is also very low because the idealizations are not justified. One can question whether astrophysical horizons can be effectively described by Virasoro methods. This is a very strong assumption to make. Comprehensiveness here is very high, though. All observables can be computed from the symmetry considerations of the Virasoro algebra. But empirical support, again, is lacking, and integration, it's also very low. The arguments for robustness are in tension with the arguments for universality. So let us go now to the last class of arguments for the universality of Hawking radiation that is based on modified dispersion relations. So these arguments were firstly suggested by Unruh in the 1980s when he worked on analog systems, and then he continued developing this kind of arguments. A very important paper on this direction is this Unruh-Schutzhul of 2005. So the idea here is that quantum effects are modeled using a modified dispersion relation. In particular, in this paper, they suggest a dispersion relation of this form, where f is a mass term that depends on the wave number. So we analyzed these arguments, and we saw that these arguments are very similar to Wilsonian arguments, in particular because this mass term, f, can be interpreted as a running coupling. And the conditions that they require in this framework are also very close to the Wilsonian conditions for renormalization group methods. In particular, they require analyticity. They assumed that when k goes to 0, the wave number goes to 0, then f goes to 0, which means that the dispersion relation is unmodified for low energy modes. They assume subluminosity, which means that the modes travel slower than the speed of light. And they also find a scaling, they define a scaling limit, which means that when k goes to infinity, this f takes constant values. So it looks very similar to Wilsonian universality arguments. And for us, these are the strongest arguments that have been offered in this to deal with the Transplanckian problem. But again, when we do the analysis, we observed that universality here is very high, but the price to pay for that is that they decrease the degree of robustness. And why is that? In particular, because they restrict the class of possible ultraviolet modifications to the physics of black holes. They seem to focus only in the k-dependent subluminal mass term, and it's questionable whether the variations in this mass term can actually capture all the possible quantum effects that might have an influence in this Hawking radiation. Universality is very high, as I said. This is the highest. They are applicable to a huge range of physical systems, eternal and astrophysical black holes, and a variety of analog black holes as well. Physical plausibility is high, fairly high. One incorporates physical features of astrophysical black holes. Comprehensiveness, though, is very low. They only focus on the occupation number of the Hawking modes. And empirical support here is actually between moderate and high, because there have been plenty of experiments in analog systems trying to prove the validity of this argument. We consider them moderate because most of the empirical evidence comes from analog systems and not from target systems, so the quality of the experiments is not, or the degree of confidence of the experiments is not as high as if we would have performed experiments in the target system, but it's moderate enough. So among the family of arguments that try to deal with the Transplanckian problem, this is the only one that has some empirical support. But integration here, again, is very low. The same features that imply that the modified dispersion relation argument can be applied in a wider range of physical situations are those that limit the robustness in the specific context of black holes. So in order to have a high degree of universality here, we again have to sacrifice robustness. So now let me conclude. So at the moment, unfortunately, the Transplanckian problem is unsolved. All the available universality arguments for Hawking radiation fail to measure up their Wilsonian counterparts. That's the result that we obtained. In particular, they fail to be integrated, which means that the arguments for robustness and universality are not consistent. We also pointed out that if the strongest part of the Wilsonian arguments was integration, and what finds in the case of in the context of Hawking radiation is that all the arguments fail to be integrated. Arguments that do well in degree of robustness do poorly in degree of universality, and arguments that do well in universality do poorly in degree of robustness, even if what we would like in order to solve the Transplanckian problem or to show that Hawking radiation is not affected by high energy physics is prove universality and robustness of the Hawking radiation. So some prospects, maybe the solution would be try to combine these different frameworks so we have in the end a consistent framework that is moderately robust and moderately universal, but at least that can do well in both camps. But to prove the consistency of that approach would be task of physicists and not of philosophers. So our work is done here. Thank you.
Questions for Professor Palacios?
Thank you. So slightly more optimistic take on the material you presented. I mean, the way you put it up is none of these arguments manage to be both robust and universal. And I look at it and I think, well, you've given me several different classes of arguments for Hawking radiation. Some of them are robust, others of them are universal. They all give the same value for the Hawking temperature. So it kind of feels as if it would be sort of, it's sort of, if there actually is Hawking radiation, it's sort of totally unsurprising that these various different arguments all succeed in giving us giving us existence of Hawking radiation at this constant common temperature and flux intensity. If there isn't any Hawking radiation, it seems kind of miraculous that these different classes of arguments with very different premises and assumptions and working on very different sort of classes of extensions nonetheless all give the same phenomenon.
Mm-hmm. Mm-hmm. Yeah. So actually, our conclusion is not as pessimistic as it looks. It's aimed to encourage more research and more consistency among these different arguments. So you're right, all of them imply Hawking radiation, but the problem is that some set of arguments are robust, imply Hawking radiation robustly, and the others universally, and there are no arguments available that are both, and what we would like is that. So I think on the basis of this sort of constant result in which you can derive under certain conditions Hawking radiation, maybe the promising way would be to combine them so we can basically use them in a coherent framework in which we can actually show, well, we deduce Hawking radiation, but we have proved that this Hawking radiation applied to different types of systems, and at the same time that this Hawking radiation would be insensitive to high energy physics or whatever quantum gravity effects. So I think, yeah, if I gave the impression that we are at a very pessimistic conclusion, it's not. It's just that we want to point out what would be desirable to have here. Thank you.
Are you saying that the physical existence of Hawking radiation is something that cannot be decided by physicists using physicists' methods, but we need philosophical analysis to determine it?
No, well, there's a caveat in this philosophical work, so that's also with Shang Grip, who is a physicist. So we are not analyzing this purely from the philosophical perspective. I don't think we can solve the problem as philosophers. I'm saying, well, with the analysis that we made, where we distinguish, for example, between terms like robustness and universality, we can help maybe research in physics. We do think that we can help research in physics. We don't think that we can solve the problem.
I mean, I think it's fair to say of the 1,000 people in the world who work on this with equations, there's an overwhelming consensus. And Unruh, who you quoted repeatedly, is possibly one of 3 people in the world who would question it. Are you doubting that consensus? Or I'm not sure what...
To which consensus are you referring?
That Hawking radiation exists.
Oh, but Unruh is not denying that.
He's what?
He's not denying that Hawking radiation exists. He's not against that consensus.
Well, he was questioning it.
No, he has made a lot of improvement in this analog experience.
Okay,
right?
so, yeah.
there's don't get me wrong. He has.
Okay, I got the impression you were saying he was questioning it.
No. This is
He's
our
questioned
conclusion.
things like that,
No,
but
no,
yeah.
no. He has given one of the proposals to put this forward, this research forward, and we are never. When we say the Transplanckian problem is yet unsolved, although on the way maybe to be solved or to be improved. We are not saying that, that we don't believe in Hawking radiation. We're just saying there is much more work to do to prove the robustness and universality of Hawking radiation. What we want to do in the end is to say that Hawking radiation is independent on quantum gravity effects, which would mean we can fairly treat Hawking radiation in a semi-classical framework without having to go to the theory, to analyze a theory that doesn't exist yet. So we also, our motivation is also super optimistic. And when we say, sorry to be repetitive, but it's important, when we see that Hawking radiation hasn't been, so the Transplanckian problem hasn't been solved, we are never casting that yet on the existence of Hawking radiation.
I mean, I think it's been solved. I think most people feel it's not.
You're welcome. Our paper is on the boundary between physics and philosophy. You're welcome to reply to this. And I don't think I have necessarily the last word on this. I would like to see the results, and I would like to see how you solve every of the complications that I mentioned, and then I will trust you, and we will revise the paper. Yeah.
And one more from Eric.
I want to make a remark in response to Andy. I mean, Andy, all honor and respect due to physicists, absolutely. But Hawking radiation has not been observed. We are nowhere near observing it. It is what I'm about to say, I'm not attributing to Patricia. This is entirely my opinion. It is entirely reasonable to be skeptical about the existence of it. One can say there's an incredible amount of theoretical evidence that supports it and is in favor of it. I am somewhat confident that it's out there. I'll bet a beer. Maybe I won't bet 2 beers, but I'll bet a beer that it's there. But to say it is completely unreasonable to doubt it, I think it's itself unreasonable.
I said, I've often made the statements in public lectures that, Hawking radiation hasn't been measured. I don't think it will ever be measured. Okay. I also make that statement that a close cousin has been, but I don't think that's strictly speaking Hawking radiation, especially since it was discovered before Hawking's
Well,
paper.
but if it's perturbations in the Sitter space-time that has a horizon, wouldn't you say it's the same physics?
I mean, it's quantum mechanics and general relativity. So, I mean, Einstein and, Schrödinger discovered it. It follows so simply. And I have not heard, lots of things that can't be measured, most things that can't be measured their existence is regularly questioned. And that's good. And I actually find it curious that the existence of Hawking radiation is so rarely questioned. This is a rare,
But let's imagine a situation where gravitational waves from inflation were detected. Wouldn't you say it's demonstrating that?
No, let me just finish my sentence. So I think it's because the argument is so simple and robust and depends on so little, and I really don't agree with the way you presented it, that those are all things which have gone over, and I think there is good reason, and we never have certainty in physics. I mean, there's no proof of the existence of the standard model, even perturbative renormalizability, yet there have been, dozen Nobel Prizes for it. We don't get certainty in physics, but at some point, things become clear enough that it doesn't seem worthwhile to very many people to, you know, there's so many things we don't understand. We can't, I'm not.
Yeah, well, as a philosopher, of course, I would agree with you that there is no certainty of knowledge on any possible aspect, right?
Yeah.
But one of the things that we do remember is to compare it with Wilsonian arguments. So that's all what we are asking for, is that we have a class of arguments that do at least moderately well in comparison to Wilsonian arguments, in which you have perfect example of universality and robustness arguments. So beyond that, we don't want to go. We don't want to go to certainty. So what we are demanding is that there are arguments that do fairly well in comparison to Wilsonian arguments.
Well, you're saying the threshold that we have in physics is too low.
Okay, so perhaps we'll defer that to later, and let's thank our speaker again for stimulating such interesting conversation. So our final speaker is Georgios Moschidis. He's a Miller Fellow at the University of California, Berkeley, working in mathematics, and he's going to speak to us about instabilities of ADS in spherical symmetry.
Well, thank you very much, Jordan, and thank you for the invitation. It's a great honor for me to speak here at the Black Hole Initiative Conference. And okay, it might not be obvious from the title, but black holes will appear in this talk. Okay. So first of all, in this talk, I will be interested about the Einstein equations with a negative cosmological constant. Now, if we add a negative cosmological constant to the vacuum equations, then okay, the simplest solution one can get is the anti-de Sitter spacetime, which I have written here down in coordinates. And okay, I chose here to stick to 3+1 dimensions. Of course, for most of the things that I'm going to talk about today, I mean, they will also hold in higher dimensions, n+1. But for notational simplicity, let's stick to 3+1 dimensions. Now, anti-de Sitter spacetime, you should think of it as the analog of hyperbolic space, let's say, from Riemannian geometry. And anti-de Sitter spacetime has a very interesting structure at infinity. So in particular, it can be conformally identified with the interior of a cylinder. So it's actually the interior of, let's say, the upper hemisphere of S3 times R, which is time. So through this conformal identification, one sees that ADS spacetime has a time-like boundary at infinity. So if we conformally identify ADS spacetime with this picture, then somehow the boundary of the upper hemisphere of S3, cross R, becomes a time-like boundary which is situated at infinity, in the sense that the value of R, the radius of the spheres of symmetry, becomes infinite at this point. And now the existence of this time-like boundary at infinity has very interesting consequences for the context in which this spacetime should be studied. So in particular, let's assume that we want to study more generally spacetimes which are asymptotically anti-de Sitter, namely that they have a similar time-like boundary at infinity. Then, exactly because the Einstein equations are of hyperbolic nature, we know that we have to study them in the context of the initial value problem. But the existence of such a time-like boundary means that in order to get a well-posed initial value problem, in analogy to what Lewis and Franz talked about in their talk, we have to also add boundary data at infinity. So this means that if we want to study the vacuum equations, we should prescribe Cauchy data on some space-like hypersurface, which should be, let's say, in analogy to the hypersurface T equals constant on ADS spacetime. And we should also add boundary data at infinity, which should be phrased in terms of the conformal geometry of this time-like hypersurface at infinity. And of course, okay, this is easier to say than to do, and establishing what are the right boundary conditions that lead to well-posedness is a highly non-trivial fact, exactly because this hypersurface lies at infinity. And the first person who actually showed the well-posedness of the initial value, who wrote down a wide class of boundary conditions that lead to well-posedness, named that lead to an initial boundary value problem which has solutions which are unique and depend continuously on the initial data, was Helmut Friedrich in 1995. So in this class of boundary data that Helmut Friedrich identified, there is a unique reflecting boundary condition, and this is the condition that the boundary is conformally flat. The cotton tensor of the boundary is 0. Okay, so now that we know that we have a class of boundary data for which the initial boundary value problem in the asymptotically ADS setting is well posed, we can pose questions about the dynamics in this setting. And the simplest question that one can ask is the stability question for the trivial solution, namely the stability question for anti-de Sitter spacetime. And Of course, the answer to this question will crucially depend on what type of boundary data one chooses at infinity, right? Different choice of boundary data will lead to different dynamics. And the question becomes really interesting when one chooses reflecting boundary conditions at infinity, when energy can no longer escape the spacetime but has to stay confined in this spacetime. And you see the expectation in the case of a negative cosmological constant is quite different than what one would expect for perturbations of the trivial solution when the cosmological constant is either 0 or positive. So remember, when the cosmological constant is 0, for example, Minkowski spacetime is known to be nonlinear stable. This is by the work of Christodoulou and Kleinerman in the early 90s. However, in this case, confinement has a very non-trivial effect on the dynamics, exactly because now perturbations are confined and the energy cannot escape. The non-linearities can be expected to lead to some turbulent behavior, and the stability question becomes highly non-trivial. So actually, in 2006, Dafermos and Holzegel made the following conjecture. The conjecture that under reflecting boundary conditions at infinity, anti-de Sitter spacetime is unstable, is non-linearly unstable under perturbations. And more precisely, they are unstable in the following way. There exists a family of perturbations for which, if one waits for long enough time, the perturbations will create a black hole in the spacetime. Now, of course, we have to specify what the black hole means in this setting, because now we're not in the asymptotically flat setting, we're in the asymptotically ADS setting. So for an asymptotically ADS spacetime, which has a time-like boundary like that, a black hole region depicted here is simply a region that cannot be seen by observers who live in the time-like boundary at infinity. It's exactly the same definition as, let's say, in the asymptotically flat setting. Of course, let me make a few remarks about the statement of the ADS instability conjecture. So first of all, the statement says that there exist arbitrarily small perturbations of the trivial initial data which lead to black hole formation. But of course, the question is, how do we measure smallness? Right? So what is, we have to measure smallness by introducing some norm at the space of initial data. And of course, we know that this norm has to be chosen so that the initial value problem defined in this topology is well posed. Otherwise, the statement is trivial. If you study perturbations which are small only in a norm which is not, where well posedness does not hold, then okay, instability is trivial to show in that case. Also, again, let me stress again that the choice of boundary conditions at infinity are very important for this conjecture. If one switches instead to dissipative conditions, and if one instead chooses optimally dissipative conditions at infinity, these are the boundary conditions when somehow, let's say, beams of energy reaching the infinity in a vertical fashion escape the spacetime and don't come back. So in this, under optimal dissipative boundary conditions, in fact, one would expect a stability statement. Actually, Holzegel, Luxemburg, Levisian, Warnick showed that at the linearized level, one has super polynomial decay of the perturbations in time. Right? So reflecting boundary conditions are important for this conjecture. And let's discuss a little bit what is known about the ADS instability conjecture so far. So until now, most of the work has concentrated in the case of spherically symmetric of matter models. So instead of looking at the Einstein vacuum equations, people have looked at the Einstein equations coupled to some matter model, which allow for non-trivial spherically symmetric dynamics. This is because studying in spherical symmetry, the problem becomes a 1 + 1 dimensional problem. It's much easier to study. And in this setting, a lot of numerical and heuristic works have appeared in the literature. So the first one was the work by Bizon and Rostvorovsky in 2011. And this work was actually, so what Bizon and Rostvorovsky did, they looked at the Einstein scalar field system in spherical symmetry. They found some perturbations which are initially very small, but which after sufficiently long time, the evolved spacetime reaches very close to a regime where a trapped surface has almost formed, the black hole region has almost formed. But they also provided a heuristic for why this instability occurs. So this is the first time that a heuristic appears. So Dafermos and Holzegel, when they made the conjecture, they didn't provide a heuristic argument. So the mechanism proposed by Bizon and Rostvorovsky is the mechanism of resonant mode mixing. So what they proposed is the following. So by doing a perturbative analysis, by assuming that we're still in a regime where the perturbation has not grown very much, what it is that they decomposed the scalar field phi into modes with respect to the eigenfunctions of the Laplacian, let's say, at t = constant slices. And because this is a nonlinear system, these modes do not evolve independently, but they affect each other. And what happens is that in the case of the Einstein scalar field system, when Dirichlet conditions are imposed at infinity for the scalar field, there are some resonant interactions in the mode. Namely, somehow there are some certain combinations of modes which somehow interact with each other, and the interaction does not have an oscillator integral that cancels in time. And they suggested that these resonant interactions are somehow the main mechanism driving the instability. And okay, following that work, there's a huge amount of literature devoted to the numerical and heuristic study of this system and the ideas instability conjecture in this setting. For example, by Buchel, Leonard Liebling, Diaz, Horowitz, Marov Santos, and many other people, many of them I haven't even listed here. However, let me stress that there is no rigorous proof so far for the ADS instability, even in the setting of the Einstein scalar field system in spherical symmetry. Now, in this talk, I want to show you a rigorous proof of the ADS instability conjecture in some matter system. But in order to do that, I will have to introduce a different instability mechanism. So you see, the resonant mode mixing mechanism, this is a mechanism that can be described at the perturbative level. But of course, if one wants to establish the ADS instability conjecture, the conjecture claims that after a long time, not only do you leave the regime, the perturbative regime, you also, the perturbations actually create a black hole region, right? So rigorous proof must be able to go all the way to showing a trapped surface formation. And in order to do that, I will first have to introduce a different instability mechanism that instead of relying on frequency space analysis and how different frequency modes interact with each other, I will instead do the analysis on physical space, assume that matter is arranged in a sequence of beams that interact with each other, and study the interaction of these wave packets in physical space. Okay, so let me first start by giving a heuristic description of this mechanism before actually going on and see how this can be turned into a rigorous proof for the ADS instability conjecture. So now this argument will be very general because it's at a heuristic level. So we will assume that we're in spherical symmetry. So we're looking at the Einstein equations coupled to matter reduced under spherical symmetry. And we'll assume that the matter model is such so that matter can be arranged, initially at least, into a large number of beams which are very narrow and ingoing in almost a null direction. Now, for example, the scalar field has this property. The scalar field can really be arranged into narrow beams, and narrow beams will propagate at least away from r equals 0 in an almost null direction. So what I will assume is that the matter model has the property that away from r equals 0, this is the center of symmetry, the very narrow beams essentially solve the Einstein null dust system. So somehow we have a very high frequency fields that somehow essentially satisfy the null dust equations. Of course, this approximation will necessarily break down close to r equals 0, close to the center of symmetry. And this is exactly because such beams near r equals 0 have to turn from ingoing into outgoing through a process which really depends on the matter model, through some pressure mechanism or some self-interaction mechanism. I mean, okay, analyzing what happens near r equals 0 will really depend on the specific properties of the matter model, but let's ignore this for the time being. And let's assume that we have initial data which are initially organized in the number of ingoing null dust beams, essentially. So these beams, as you can see from this picture, what will happen is that these beams initially will be ingoing. They will interact in some places close to r equals 0. Then they will all become outgoing. They will be reflected at infinity because we have assumed reflecting boundary conditions at infinity. They will interact again here, and this process will go on for a long time. Okay, so what we want to do is that we want to analyze how these beams exchange energy with each other. So first of all, how do we measure the energy of the beams? We will measure the energy of the beams with the use of the Hawking mass, of course. Now, remember, we will assume that most of the matter is contained in these matter beams. So the regions between the beams here, so let's say this region or this region, these are approximately vacuum regions. So the renormalized Hawking mass, we will assume that it's constant. That it's constant in those regions. And remember, we want to show that at some point a black hole region forms. So we want to show that there exists a time where somehow 2m over r, m now is the Hawking mass, r is the radius function, exceeds 1. If we find such a point in the spacetime, then we know that we have a trapped surface there, and therefore we're inside the black hole region. Okay, so for each beam, we will define its energy simply as the difference of the value of the normalized Hawking mass in the vacuum regions bounding this beam, right? This is somehow, this is why the Hawking mass is important. And we should know that the energy of each beam, so if I call a beam, let's say zeta, then the energy of zeta will, of course, change every time the beam intersects another beam because of nonlinear interactions, but this energy will not change upon reflection at infinity, exactly because of the reflecting boundary conditions imposed there. Okay, so now let's zoom into two interacting beams. So let's go, so in this picture, let's just move into a region where two of these beams interact. And let's assume that the interaction region is still inside the regime where the null-dust approximation holds, where somehow the beams satisfy the Einstein null-dust system. And let's try to use these equations to calculate the difference of the energy of the beams. Now, in the null-dust, for the Einstein null-dust system, this is a very convenient system to work with because most of the equations actually reduce to transport equations. So if we want to, can I use, it's okay. It's okay. So if we want, let's say, to calculate the energy of this beam, which is again the difference of the Hawking mass in the two vacuum regions here, we simply have to calculate how the difference of what is the derivative of the Hawking mass in the v direction and how much it changes in the du direction. Right? So by integrating the equation for this term, which in the Einstein null-dust system, this is a very simple equation to work with, we readily obtain that the energy of the ingoing beam increases by a factor which depends on the energy of the outgoing beam, and it becomes strong. And this increase becomes stronger when we are close to r equals 0, when we are close to the center of symmetry. And of course, by the conservation of the total energy of the beams, we know that the energy of the outgoing beam must decrease by an analogous factor here. So what does this tell us about the configuration of beams? So now let's go back to the configuration of beams. Let's just assume at this moment that we have just two beams of matter. So initially we have two beams of matter. Initially they are ingoing. They interact here. At this interaction, the ingoing beam increases its energy. The outgoing beam decreases its energy, right? And the interaction happens close to r equals 0. So this exchange of energy is relatively big. Then these beams will interact again near infinity. Now the top beam will be outgoing. So this means that it will lose energy to the other beam. But because the interaction takes place close to infinity, this means that the interaction is weaker. So the energy that will lose at this point, that the top beam will lose at this point, will be much smaller than the energy that it had gained before. So all in all, we see that between two successive reflections at infinity, the top beam will have gained energy from the bottom beam, right? So what does this tell us? This tells us that in a configuration of many beams, energy will flow from the bottom beams to the top beams. And now, if we were careful to arrange initially the beams so that the top beams were narrower than the lower ones, this is a mechanism that allows energy to flow from large scales to small scales, right? So you can suspect that this is an instability mechanism, because remember, in order for a trap surface to form, we want energy to flow at sufficiently small scales after some time. Okay, so this is a heuristic mechanism that somehow is different than the resonant mode mixing mechanism. And let's see how this mechanism can be applied to give a rigorous proof of the ADS instability conjecture for some matter model. So the matter model that I will discuss now is the Einstein massless Vlasov system. Now, the Einstein massless Vlasov system is simply the system where the Einstein equations are coupled to a Vlasov field. Now, a Vlasov field is a function which is defined not on the manifold M, but on the tangent space. So it takes a value for each point of the spacetime and for each direction on that point. And the Vlasov equation is simply the equation that simply tells us that this field is conserved along the geodesic flow. So the value that, if we take the value of the field at some point in some direction, then along the geodesic, which starts from this point and goes in this direction, this field will have the same value. And okay, this is a system that somehow one can study in spherical symmetry. It has non-trivial dynamics, but also this system, it has an unexpected connection, if you want, with the vacuum equations themselves in the high frequency limit. So more precisely, if you want, this is aside. There was a conjecture by Bournet, I think in his thesis in 1989, who claimed that if one has high frequency limit of spacetime solving the vacuum equation, so if we have, let's say, families of vacuum spacetimes which converge to some limit, some high frequency limit, so somehow the convergence is only in some low regularity node, and not a high one, then the limiting spacetime will not necessarily solve the vacuum equations, because now this is a weak limit, but it will solve the Einstein massless Vlasov system for some Vlasov distribution. And of course, Bournet also claimed the opposite, that any solution of the massless Vlasov system can be approximated by a vacuum solution in a weak sense. So, I mean, not much is known about this conjecture. Huneau and Luke have a lot of work on this conjecture in the axisymmetric polarized case, but I don't want to stay on that. I just want to mention this connection of this system with the vacuum equation. And now, why do I choose this system to apply this mechanism? This is because for the Einstein massless Vlasov system, it's very easy to arrange matter into localized beams, and the region between the beams will be exactly vacuum, so I don't have to estimate, let's say, error terms occurring from tunneling. And for this system, we can rigorously prove the ADS instability conjecture in the spherical symmetry setting. Namely, we can show that there exist spherically symmetric perturbations of the trivial initial data for the Einstein massless Vlasov system, which are small with respect to a norm, a scale invariant norm for which well-positedness holds. Let me not say more about the norm, but it's a good norm for this problem, and which have the property that if one waits for sufficiently long times, then a black hole region will form for any member of this family of perturbations. So in particular, anti-de Sitter spacetime is unstable for this system in this norm. And I just want to remark that, this norm is a norm for which well-positedness holds, so it makes sense to ask this question in this initial data topology. And you might be worried that I'm not showing to you this norm. I told you that this norm is scale invariant, so it's a little bit of it's of low regularity. So you might worry that this instability that I described to you is an effect of this low regularity of the norm, and not somehow really an effect of confinement. But I will argue that this is not the case, because if one, let's say, tried to look at perturbations of Minkowski spacetime for the Einstein massless Vlasov system in spherical symmetry, which are small in this norm, then Minkowski spacetime is stable for small perturbations in this norm. So this norm somehow is a good norm to capture the instability of anti-de Sitter spacetime. It doesn't insert new pathologies to the system. So how would one turn the previous heuristic argument into a rigorous proof for this model? So first of all, what we do is that we have to choose our initial data. Here, I chose the initial data to be characteristic initial data, lying on a characteristic surface. But you can very easily choose similar data on a t equals constant surface. So we choose the initial data so that initially the Vlasov field is arranged into a very large number of ingoing beams. So you see, initially matter will move ingoing. And of course, as we said, the further up we go, the narrower the beams must become. And I also choose the narrower beams to be supported on geodesics which have smaller and smaller angular momentum. Now, this has the effect that the narrower beams here, because they're supported on geodesics with smaller angular momenta, they will approach closer to the center r equals 0, right? And so what we want to show that in the end, the narrower beams attain enough energy, and this energy will reach to regions which are sufficiently close to r equals 0 so that the trap surface is formed. Right? So this is how we set up the initial data. And then, at least for small times, exactly because our initial data are small in a well-posed norm, we know that our spacetime will be, at least for small times, close to anti-de Sitter spacetime, and the previous heuristic that we talked about how these energies exchange, how these beams exchange energy, this will hold true. But we will have to show that these heuristics remain true all the way up to the regime of black hole formation. And there are many technical difficulties that one has to tackle, which I'm not going to get into detail. So first of all, one has to be able to control the geodesics and the beams in a low regularity setting, which somehow one really has to use properties like similar to the null condition for the structure of the equation. Let me not get into that. Now, there is a more important conceptual difficulty, which appears at the point when you leave the perturbative regime, which is the following. So for the Einstein massless Vlasov system, we know that if energy is concentrated at sufficient scales, which are yet not enough to give a black hole formation, but are not too small, then one can have so-called static stars. So what can happen when 2m over r goes above a threshold? It can happen that an ingoing beam might remain close to r equals 0 for a long time, approximating a static star, and not going back to infinity quick enough. So somehow such a thing would destroy our configuration of beams. So okay, we have to be very careful in how we design the initial data so that we really avoid such pathologies. But I will not say more about that. Let me just say that this mechanism that I told you about, so this gives a rigorous proof for the case of the Einstein-Masters-Vlasov system, but I expect it to also be applicable to the case of the Einstein scalar field system. The problem is that one has to be it's technically more demanding, but the basic idea should be applied in this case. And also a similar mechanism should also be applicable to the vacuum equations in 4+1 dimensions, because now in 4+1 dimensions, we can reduce the equations under the biaxial Bianchi-9 symmetry class. So this is, the resulting system of equations is similar to the Einstein scalar field system in 3+1 dimensions. So similar arguments should probably apply in that setting. And of course, the big challenge is how can one prove, what are the right arguments that one can use to prove the ADS instability conjecture for the vacuum equations in 3+1 dimensions when no symmetry reduction to 1+1 dimensions can hold, right? So let me finish my talk here. Thank you very much for your attention. And since I'm the last speaker, of course, I also have to thank the organizer for this conference. But,
Questions for Georgios?
So it seems like in this mechanism, there's no role for the resonant frequencies of the
exactly. So that's a good.
Yeah, but so so would this mean that there are systems where this?
So let's say, for example, okay, in order to, we have to, let's say, apply this mechanism now to the case of the scalar field in order to be able to somehow make the comparison with the resonant mode mixing. So what I would, so you're right. I don't see this, let's say, the resonant structure of the spectrum for this mechanism, which somehow, in the case of the Einstein scalar field system, you know that when you impose Dirichlet conditions at infinity, you have resonant spectrum. If you impose Neumann conditions, maybe the resonant spectrum is destroyed. I would expect, so this mechanism should be present in both cases. I would expect that this mechanism actually takes a longer time to kick in than the resonant mechanism. So somehow, okay, this is a conjecture, I don't know, I haven't checked, but I would expect that if you have, you know, like, if the spectrum is resonant, then that mechanism will kick in faster than this mechanism that I described. But somehow this mechanism is always there. Somehow, even if you don't see, you know, like a resonant interaction at a time scale, which is what is it for resonances, this might be there for.
So you have no control on the time scales.
So it's very difficult to set the time scale for the very simple reason. So you see, I mean, the answer to that would be that somehow this instability kicks in a time scale, let's say, of this order, when the size of the initial data are of that order. But now, the size of the initial data, how they're measured with the norm, and the choice of the norm will really affect that. Now, in the case of the resonant mechanism, what people do is that they take a fixed profile, and they multiply this by epsilon, and then they look at the dependence of the time scale on epsilon. Now, whatever initial norm you use, for that profile, you know that the size will be of order epsilon, right? But in my case, my profiles are not rescalings of the same profile. They are very different. So it's very difficult somehow to really make this. I mean, what is epsilon in this case? You have to. But yeah, so I don't know how to phrase this correctly.
It would be interesting because, for instance, if you take a star, now it's a confining system, like fluid fluctuations inside the star. This would then seem to imply that at some point, you should get collapse. I see. Very good.
Other questions for Georgios?
What can you say about the case outside of spherical symmetry? Would this mechanism will be of use in that case?
You could, I mean, you know, I can't give you a rigorous answer, but I would imagine yes. I mean, in the sense that you could imagine that outside spherical symmetry, you could have beams of gravitational waves which are almost, you know, like they're not symmetric, but they're in some sense homogeneous in the spherical direction, and they have the form of a pulse in the radial direction. And these interact with each other. So you could imagine that the same mechanism applies. Of course, now the question is, what is the right space of initial data that captures this type of perturbations? Do you have well positiveness in this space? And of course, there are all, you know, like the questions, you know, how do you really propagate in the vacuum case these type of perturbations, you know, when they are reflected at infinity, you know, how do you say that? But at a very, like at a very high level, the heuristic level, I would expect that, yeah, it's relevant, but yeah. That's it.
Further questions? Okay, if not, we're going to move on to some comments from our director, Avi Loeb, and since Georgios is the last speaker, we'll thank him and all the other speakers over the past 3 days. Thank you.
So first, I wanted to express my gratitude to all the speakers and members of the audience for having such a stimulating conference. People come from different disciplines, mathematics, physics, philosophy, and astronomy. And each community brings their expertise, and they speak different language, but nevertheless, we managed to create a culture here at the Black Hole Initiative that promotes, that is more than the sum of the parts. That's the most important thing. And I found the discussions during the conference extremely stimulating on all fronts. But I just wanted to, and I also wanted to extend a very warm welcome to any of you to come again to the Black Hole Initiative in the future. We would love to have you as a visitor, and we're very likely to be funded for another 3-year period. So keep that in mind and visit us here at Harvard again. I just wanted to highlight one of the fields as being extremely important. I mean, in fact, just half an hour ago, we had a discussion on this issue, and we had 2 philosophers today discussing important aspects of physics. And in my view, philosophy and the philosophers that work on issues related to black holes serve a very important purpose. They're sort of like the canary in a cave, telling us of the risks of sometimes not being fully honest with ourselves, not defining things properly. And, it's just like architects that try to come up with a blueprint for how to do the job well and how to accomplish the task of physics. And you don't need many architects compared to the number of engineers or the number of construction workers that you employ when you make a building. But they serve an extremely important role. And I think if you wanted to make an analogy, there is an excellent analogy with supermassive black holes. They do not make up a big fraction of the mass of a galaxy. They sit at the center, they make up less than 0.1% of the mass, but they have a huge influence on the evolution of galaxies. And you don't need to make up a big fraction of the community, but at the same time, you could play an extremely important role in shaping the intellectual conversation that we have. And I do think that the philosophers serve a very important purpose of outlining why some of the discussions we have are not necessarily fully justified in having the confidence that we have as physicists in their validity. And I wanted to encourage the philosophers in the audience to continue contributing. In fact, in a previous conference, one of the philosophers argued that if the physicists agree for a period of 10 years on something, it must be right. And I couldn't find this statement more wrong than this one, actually, because there are many examples in the history of physics where communities of physicists, due to social pressure, psychological pressure, herd mentality, agreed on something that ended up being wrong. And many things in the mainstream of physics were proven wrong over the years. The most recent example is, that supersymmetry will be demonstrated with the Large Hadron Collider. That was a theme of decades of studies in mainstream theoretical physics, and supersymmetry was not found in the Large Hadron Collider. And ultimately, we have a dialogue with nature. it's not a monologue, and nature tells us how to proceed. And the experiments serve a very important role, but at the same time, we should be honest with ourselves. If a lot of us agree on something, it doesn't mean that it's right. And I think casting a doubt on some concepts because they were not yet demonstrated experimentally is fairly legitimate, as we heard this morning. So altogether, I think we have a thriving community, and I would very much encourage all of us to continue interacting with each other. I think we are making much more progress than if we were isolated in our silos. And so thank you for participating in this dialogue.